Welcome to Sleepy Scientist Stories, where we explore the most fascinating mysteries of our universe in a way that's both relaxing and mind-expanding. Tonight, we're embarking on a gentle journey through time and space to discover what the James Webb Space Telescope has revealed about the earliest moments of our cosmos. In 2022, humanity gained an extraordinary new perspective on the ancient universe. The James Webb Space Telescope began transmitting its first images, breathtaking, intricate views of cosmic structures far more ancient than anything previously observed. Through its remarkable infrared capabilities, JWST peers across more than 13 billion years of cosmic history, collecting the delicate light emitted by the universe's first stars and galaxies. For countless generations, the origin story of our universe has remained one of science's greatest enigmas. Now, for the first time in human history, we're witnessing this cosmic birth story unfold before our eyes. The discoveries we're making are fundamentally reshaping our understanding of how everything began. Before we drift into tonight's cosmic exploration, let us know in the comments where you're listening from and what time it is in your corner of the world. Settle in comfortably as we embark on this mesmerizing journey to explore what the James Webb Telescope discovered at the very edge of existence. In those initial moments following the Big Bang, our universe resembled a churning ocean of pure energy and microscopic particles dancing in complete chaos. The temperature was incomprehensibly hot, trillions upon trillions of degrees, so extreme that even the simplest atoms couldn't maintain their structure, let alone complex formations like stars or planetary bodies. For hundreds of millions of years, the cosmos remained in this luminous, dense state as it gradually expanded and cooled through the vast emptiness of space. Then, approximately 400 million years after that primordial explosion, something truly remarkable occurred. The first atomic structures began forming, creating hydrogen and helium, the fundamental gases from which all stars are born. Gravitational forces slowly drew these gases together, and in this cosmic dance, the universe's first stars ignited. These stellar pioneers gathered into the earliest galaxies, illuminating a cosmos that had been shrouded in darkness for eons. This extraordinary period is known as the Cosmic Dawn, and it's precisely what the James Webb Space Telescope is now observing with unprecedented clarity. It's capturing light and data from when the very first galaxies began to shine, helping scientists unlock the mysteries of our most distant past. The James Webb Space Telescope represents something entirely unique in human engineering and scientific ambition. Launched on December 25, 2021, it now orbits our Sun at a specially chosen location called the Second Lagrange Point, or L2. This position sits about 1 million miles from Earth and provides the perfect balance for keeping the telescope stable and extraordinarily cool. Being positioned so far from our planet also shields it from Earth's heat and brightness, allowing for crystal-clear observations of deep space. What makes JWST particularly revolutionary is its ability to perceive infrared light. While most telescopes rely on visible light, infrared radiation can penetrate through cosmic clouds of gas and dust, revealing hidden stars and galaxies that were previously invisible to us. Even more significantly, infrared light enables JWST to observe the oldest stars and galaxies in existence. As our universe expands, light from distant objects stretches into longer wavelengths, shifting from visible light into the infrared spectrum. This phenomenon is called cosmological redshift, and the farther away an object is, the more its light becomes stretched. Because JWST is specifically designed to detect these faint, elongated signals, it can peer deeper into space and further back in time than any instrument before it. It functions almost like a cosmic time machine, showing us the universe as it appeared more than 13.5 billion years ago, just a few 100 million years after the Big Bang occurred. So JWST isn't simply capturing beautiful photographs. It's helping us understand how stars were born, how galaxies formed, and how everything we observe today had its beginning. When JWST transmitted its first images back to Earth, the scientific community was absolutely astounded. The telescope had gazed deep into the cosmic void and captured something incredible, galaxies forming just a few 100 million years after the Big Bang. At that time, the universe was still incredibly young, yet what JWST revealed was a sky bustling with activity. Scientists had anticipated seeing only a few small primitive galaxies, but instead they discovered many more than they ever imagined possible. These galaxies appeared in all sorts of unexpected shapes and sizes, suggesting that the early universe was far more active and full of surprises than previous theories had predicted. One of the most significant discoveries was the detection of proto-galaxies, the first small clusters of stars that would eventually merge to form the massive galaxies we observe today. These early galaxies weren't neat and orderly like the spiral or elliptical galaxies we're familiar with now. They were chaotic, irregular, and wild in their structure. Stars were being born at incredible rates, bursting into existence in enormous numbers. This completely changed how scientists think about galaxy formation. It became clear that galaxies didn't form slowly and quietly over vast periods of time. Instead, they were born in a cosmic rush during an extremely turbulent and active period. But JWST's discoveries didn't stop there. It's also finding evidence of the universe's very first stars, known as population 3 stars. These primordial stars were completely different from any stars we see today. They formed from the simplest materials available, primarily hydrogen and helium left over from the Big Bang itself. They contained no heavier elements like carbon or iron, which are common in modern stars. Scientists believe these stars were enormous, much larger than our Sun, and they burned incredibly hot and bright. Because they lacked heavy elements to help regulate their nuclear processes, they consumed their fuel rapidly and lived short but spectacular lives. When these massive stars reached the end of their life cycles, they exploded in supernova blasts, some of the most powerful explosions the universe has ever witnessed. These cosmic detonations scattered the first heavy elements into space, materials that would later become essential for forming new generations of stars, planets, and eventually life itself. By finding evidence of these long-lost stars, JWST is helping scientists piece together how the universe transformed from a simple, element-poor environment into the rich and complex cosmos we inhabit today. Another major breakthrough facilitated by JWST involves studying two of the universe's most perplexing mysteries: dark matter and dark energy. These strange, invisible components make up approximately 95% of the entire universe, yet we still don't fully comprehend their nature. Dark matter doesn't emit light or energy, making it impossible to observe directly. However, JWST helps scientists determine where it exists by observing how it bends and distorts light from galaxies positioned behind it. This effect is called gravitational lensing, and it allows astronomers to map out where dark matter might be hiding and how it influences the growth and evolution of galaxies. You can think of dark matter as the invisible scaffolding that shapes the large-scale structure of the universe. Then there's dark energy, the mysterious force that's causing the universe to expand at an accelerating rate. By using JWST to measure how rapidly galaxies are moving away from us, scientists are gathering crucial data about how dark energy operates. This research could help us answer one of the most profound questions in science. Will the universe continue expanding forever, eventually slow down, or someday collapse back in on itself? JWST isn't only focused on the distant past. It's also searching for signs of life beyond our own planet. One of its most exciting missions involves studying exoplanets, worlds that orbit stars outside our solar system. Some of these distant worlds might possess the right conditions to support life as we know it. JWST can analyze the gases present in their atmospheres and search for telltale signatures. If it detects water vapor, that could indicate the presence of clouds and possibly even precipitation. If it finds methane, scientists will investigate whether it originates from geological processes like volcanic activity or from biological sources like living organisms. And if JWST discovers oxygen in significant quantities, it might suggest that plants or other life forms are producing it through photosynthesis. If we ever confirm that life exists beyond Earth, it would completely revolutionize how we understand the universe and our place within it. One of the most surprising discoveries made by the James Webb Space Telescope involves the supermassive black holes found at the centers of some of the oldest galaxies in the universe. These galaxies formed only a few 100 million years after the Big Bang, roughly 13 billion years ago. Based on current scientific understanding, black holes that young shouldn't have grown to enormous sizes yet. There simply hasn't been enough time for them to accumulate such massive amounts of material. But JWST has revealed something puzzling and unexpected. Some of these ancient black holes are already incredibly massive, far larger than they should theoretically be for their age. This startling finding has left scientists questioning fundamental assumptions about black hole formation and growth. It suggests that black holes may not develop slowly over billions of years as previously believed. Instead, they might form and expand much more rapidly than any current theory can adequately explain. This discovery is forcing astronomers to completely reconsider the basic principles of how black holes are born and how they evolve over cosmic time. It challenges many long-standing ideas about what the early universe was like and serves as a reminder that the cosmos is still full of profound mysteries waiting to be unraveled. Thanks to the James Webb Space Telescope, we're only beginning to uncover these cosmic secrets. To truly appreciate how such remarkable discoveries are possible, we need to examine the telescope itself more closely. The James Webb Space Telescope represents a masterpiece of modern science and engineering. At the heart of this incredible machine lies a massive mirror coated with an ultra-thin layer of gold, stretching more than 21 feet in diameter. This mirror is specifically designed to capture the faint, invisible infrared light that has been traveling across space for billions of years. The mirror isn't constructed as one large, solid piece. Instead, it's composed of 18 golden hexagonal segments that unfolded one by one, like a giant metallic flower blooming in the vacuum of space. When these segments locked into their precise positions, they formed a stunning honeycomb pattern, both structurally strong and elegantly delicate. This ingenious design allows the telescope to gather as much light as possible from some of the most distant and ancient objects in the universe. But that's only the beginning of JWST's capabilities. The telescope also carries a sophisticated array of instruments, advanced cameras and devices called spectrographs, that can peer deeper into the universe than ever before. These tools don't simply take photographs. They break down the light from stars and galaxies into its component colors, much like separating white light into a rainbow. By analyzing this decomposed light, scientists can determine what these celestial objects are made of, how fast they're moving through space, and precisely how far away they are located. It's almost like conducting a cosmic form of archaeology, excavating through layers of ancient light instead of earthly sediment, uncovering secrets that have been buried in time for billions of years. But JWST isn't just a brilliant piece of machinery, it's also the result of an extraordinary international collaboration. Although NASA led the mission, it wasn't working alone. The European Space Agency, known as ESA, and the Canadian Space Agency, or CSA, made crucial contributions to the project. ESA provided essential scientific instruments, while CSA contributed cutting-edge technology and helped fund the ambitious undertaking. Together, these space agencies transformed a bold dream into concrete reality. The James Webb Space Telescope stands as a shining example of what humanity can achieve when nations unite with a shared goal to better understand the universe we all inhabit. Thanks to this international teamwork, JWST has already begun revolutionizing how we perceive the cosmos. And what's even more exciting is that this is just the beginning of its mission. The telescope is expected to continue transmitting invaluable scientific data for many years to come. Every new discovery will generate additional questions, inspire further research, and encourage a new generation of scientists to literally reach for the stars. JWST isn't the only groundbreaking mission on the horizon either. More amazing tools are currently in development. The Nancy Grace Roman Space Telescope, for example, will help us probe even deeper into the mysteries surrounding dark energy and dark matter. The European Extremely Large Telescope, which will be positioned high in the Chilean mountains, will provide even sharper images of distant galaxies and stellar formations. These new observatories, working in conjunction with JWST, will help construct an even clearer picture of the universe, from how it all began to where it might be heading in the distant future. These discoveries represent far more than just scientific achievements. They're about connection and understanding our place in the cosmic story. They link us directly to the very beginning of time, to the ancient stars that forged the elements present in our bodies, and to the primordial galaxies that shine like tiny sparks scattered across the vast darkness of space. They remind us that we are part of something immeasurably greater, something beautiful and mysterious beyond our everyday comprehension. By peering back in time more than 13.5 billion years, the James Webb Space Telescope allows us to witness the birth of the cosmos itself. The universe is unimaginably vast, and for hundreds of years, scientists have been working tirelessly to uncover its deepest mysteries. They've posed fundamental questions like, where did everything begin? How did it all start? And how has the universe changed and evolved over cosmic time? One of the most mysterious and important pieces of evidence in this cosmic investigation is a phenomenon called redshift. This strange effect helps scientists understand how the universe has been stretching and expanding ever since it first came into existence. To really understand what redshift means, we need to consider something fundamental: light itself. Light travels in waves, similar to the ripples that spread outward when you drop a stone into a calm pond. These waves can be short or long, and each wavelength appears to us as a different color. For example, shorter wavelengths make light appear blue, while longer wavelengths appear red to our eyes. When scientists study light emanating from stars, galaxies, and other cosmic objects, they can measure these wavelengths to learn more about the sources of that light. This is where redshift becomes crucial to our understanding. Redshift occurs when light's wavelength gets stretched out. So instead of appearing blue or its normal color, the light shifts toward the red portion of the electromagnetic spectrum. Think about the familiar sound of a car driving past you on the street. As it approaches, the sound waves are compressed and the pitch seems higher. But as it moves away, the sound waves are stretched and the pitch drops, becoming lower. This is called the Doppler effect, and light behaves in a remarkably similar way. When an object in space moves away from us, the light waves it emits get stretched out, causing that light to appear more red than it normally would. That's redshift in action. In the vast expanse of outer space, when galaxies or stars are moving away from Earth, the light they send toward us becomes stretched during its journey, producing this redshift effect. The faster something is moving away from us, the more its light becomes stretched, and the stronger the redshift becomes. This shift serves as a powerful diagnostic tool. By carefully measuring redshift, scientists can determine how fast a galaxy is moving and calculate how far away it is from us. Redshift has been instrumental in helping us understand that our universe isn't static or unchanging. It's continuously growing larger, expanding in all directions. The concept of redshift is intimately connected to one of the most important discoveries in the history of astronomy. Back in the 1920s, an American astronomer named Edwin Hubble was systematically studying distant galaxies when he made an astounding discovery. These galaxies weren't simply sitting motionless in space, they were actively moving away from Earth. Even more surprising was the pattern he observed. The farther away a galaxy was located, the faster it appeared to be receding from us. This relationship became known as Hubble's law, which tells us that the universe is expanding and that galaxies at greater distances are racing away from us at higher speeds. This groundbreaking discovery provided scientists with one of their strongest pieces of evidence supporting the Big Bang theory. According to this theory, our universe began as an infinitesimally tiny, extremely hot and dense point approximately 13.8 billion years ago. Since that initial moment, it has been continuously stretching and expanding outward in all directions. As galaxies move away from us due to this expansion, the light they emit becomes stretched during its long journey to Earth, which is why we observe it as redshift. By analyzing how much light from a galaxy has been shifted toward the red end of the spectrum, astronomers can estimate how far away that galaxy is located. The greater the redshift, the faster the galaxy is moving away from us, and the more distant it must be. So when we observe redshifted light, we're not just seeing where a galaxy currently exists in space, we're actually looking backward through time itself. This is because light from faraway galaxies takes an enormous amount of time to reach us across the vast distances of space. The more redshifted the light appears, the longer it has been travelling through the cosmos, and the farther back in time we're actually observing. This brings us to something truly extraordinary. Redshift doesn't just help us understand how fast galaxies are moving away from us. It also provides us with a unique opportunity to observe the universe as it existed billions of years ago. When we study very distant galaxies, we're seeing them not as they are today, but as they were when the universe was still young and just beginning to evolve. This is because their light has been travelling through space for over 13 billion years to reach our telescopes. The deeper we peer into space, the farther back in time we're able to see. The galaxies with the highest redshift values are the ones that are farthest away from us, which means they are also the oldest ones we can possibly observe. These ancient galaxies formed only a few 100 million years after the Big Bang occurred. Studying them helps scientists understand how the very first stars and galaxies came into being. It's like peeling back successive layers of cosmic time to witness the universe's evolution from a small, hot, crowded environment to the vast, star-filled cosmos we know today. These high redshift galaxies function like cosmic time machines, offering rare and precious glimpses into the universe's earliest epochs. To study them effectively, astronomers employ powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope. These sophisticated instruments are specially designed to detect the incredibly faint light from galaxies that are billions of light years away from Earth. When astronomers carefully examine the light from these distant galaxies, they can measure exactly how much it has been stretched during its journey to us. The more the light has been stretched, the older it is, and the farther away the source galaxy must be located. This stretching occurs because our universe has been continuously expanding ever since the light originally left those ancient galaxies. So when we look far out into the depths of space, we're simultaneously looking far back into the history of time itself. This is how scientists can study galaxies that formed just a few 100 million years after the Big Bang, when the universe was still in its cosmic infancy. These early galaxies were dramatically different from the ones we observe in our modern universe. Galaxies from the early universe were much smaller and far more chaotic in structure. They hadn't had sufficient time to grow into the large, well-organized galaxies we see scattered across today's night sky. Instead, they were still actively forming new stars and gravitationally pulling in surrounding gas and dust. These infant galaxies were often lumpy, irregular, and poorly organized compared to their modern descendants. They didn't possess the neat spiral arms or smooth elliptical shapes we typically associate with mature galaxies. In those early cosmic times, galaxies were also frequently colliding with each other and merging into larger structures. These cosmic collisions were actually extremely important for the universe's development. They helped shape the galaxies we see today and triggered intense bursts of star formation throughout the early cosmos. Without those chaotic early mergers and interactions, we wouldn't have the beautiful, complex galactic structures we observe in our present-day universe. So by studying galaxies with high redshift values, astronomers can essentially travel back billions of years in time to witness how the universe began, how the first stars and galaxies were born, and how everything evolved from a tiny, fiery beginning into the grand, sprawling cosmos we inhabit today. One of the most thrilling aspects of studying these extremely distant, high redshift galaxies is that they provide us with a unique window into the era when the universe's very first stars came into being. These primordial stars are called population 3 stars, and they likely formed relatively soon after the Big Bang, which occurred approximately 13.8 billion years ago. During that ancient time, the universe was still incredibly young and consisted almost entirely of just two fundamental gases, hydrogen and helium. As cosmic time progressed, gravitational forces gradually pulled these gases together into increasingly dense clumps. Over millions of years, these gas clouds grew heavier and more concentrated until they eventually collapsed under their own gravity, igniting nuclear fusion for the first time and creating the universe's first stars and galaxies. But these early stars were profoundly different from any stars we can observe in today's night sky. They were far more massive than typical modern stars, burned at much higher temperatures, and consumed their nuclear fuel at dramatically faster rates. Unlike contemporary stars, which contain a complex mixture of elements like carbon, oxygen, nitrogen, and iron, these ancient stars were composed almost entirely of primordial hydrogen and helium. They contained virtually none of the heavier elements that are so crucial for planet formation and the development of life as we know it. When these massive first-generation stars reached the end of their relatively brief lifespans, they exploded in catastrophic supernova blasts that released tremendous amounts of energy and created the first heavier elements in cosmic history. These stellar explosions produced elements like carbon, oxygen, silicon, and iron, then scattered these newly forged materials throughout space, where they would eventually become the essential building blocks for subsequent generations of stars, planetary systems, and ultimately biological life. The lives and deaths of these first stars represent some of the most pivotal moments in the entire history of our universe. They fundamentally transform the cosmos from a simple, element-poor environment into something far more complex and chemically rich, setting the stage for everything that would follow, including the eventual emergence of planets capable of supporting life. By studying galaxies that are extremely far away in both space and time, scientists are learning more about these ancient stars and beginning to understand how they forever changed the character of our universe. These primordial stars also played a crucial leading role during an essential period called the Epoch of Rhionization, which occurred several 100 million years after the Big Bang. At that time, the universe was largely dark and filled with a thick, opaque fog of neutral gas that blocked most light from traveling freely through space. But as the first stars began to shine with intense ultraviolet radiation, their powerful light interacted with this cosmic fog and caused the gas atoms to become ionized, meaning their electrons were stripped away from their nuclei. This fundamental change had profound consequences for the entire universe. Suddenly, light could move much more freely across vast cosmic distances, making the universe transparent and allowing electromagnetic radiation to travel unimpeded. This transformation marked the beginning of the bright, clear universe we observe today, where light from distant objects can reach us across billions of years and light-years of space. Now, you might wonder, how exactly do we observe these incredibly ancient stars and galaxies if they're so unimaginably far away in both distance and time? This is where the remarkable capabilities of modern space telescopes become absolutely essential to our understanding of cosmic history. This is where redshift becomes our cosmic storyteller. Redshift isn't like the fantastical time travel we see in science fiction movies, where adventurers leap into gleaming machines and zip through temporal corridors. Instead, it's a beautifully elegant scientific method of peering back through the ages using nothing more than the light that surrounds us. When we gaze deep into the velvet darkness of space, we're actually observing light that departed those distant galaxies millions or even billions of years ago, carrying with it the secrets of ancient times. Because our universe has been steadily expanding since that first moment of the Big Bang, this ancient light becomes stretched during its incredibly long journey to reach us, making it appear more red in color, hence the poetic name redshift. The farther away a galaxy lies from us, the more dramatically its light becomes shifted toward the red end of the spectrum, and the older the cosmic image we're witnessing becomes. So by studying these red-shifted galaxies, astronomers are essentially looking backward through time itself. It's like watching a magnificent cosmic movie playing in reverse, revealing how the universe appeared when it was much younger and more turbulent. This ancient light acts like a gentle message from the distant past, carrying within its wavelengths precious clues about how stars and galaxies first formed, how the universe gradually changed and evolved, and even hints about how it might continue to transform in the eons to come. When we observe galaxies like Andromeda, which lies more than 2 million light-years away from us, or peer at even more distant cosmic structures, we're seeing them exactly as they were millions or billions of years ago. This means the light currently reaching our eyes today has been traveling through the vast emptiness of space since long before humans ever walked the Earth. It's a profound reminder of just how immense the universe truly is, and how wonderfully small we are in comparison to the cosmic tapestry that surrounds us. Redshift provides scientists with one of their most powerful tools, for unlocking the mysteries of the early universe. With every new discovery, we move closer to answering some of the most fundamental questions that have puzzled humanity for centuries. How did the very first stars and galaxies come into existence? When did black holes begin their incredible growth? Could there be life flourishing on other distant planets, or even signs of alien civilizations patiently waiting to be discovered? In the coming decades, scientists expect to learn even more by employing increasingly advanced telescopes and sophisticated instruments. These remarkable tools might help us locate the universe's first black holes, understand how galaxies grew and evolved over cosmic time, and perhaps even detect clear signs of life beyond our own precious Earth. Redshift is far more than just a simple shift in color. It's like having a time machine constructed entirely from light itself. It helps us peer back to the very beginning moments of the universe's existence. These distant galaxies function like cosmic time capsules, holding the deepest secrets of creation safely within their ancient starlight. By carefully studying their light, we get to witness the birth of stars, the formation of galaxies, and the grand unfolding of cosmic history itself. Galaxies are truly gigantic collections of stars, gas, cosmic dust, and something wonderfully mysterious called dark matter. All of these components are held together by gravity, the same fundamental force that keeps our feet firmly planted on the ground here on Earth. Galaxies come in many different shapes and sizes, each with its own unique character and story to tell. Some galaxies, like our own beautiful Milky Way, are spiral-shaped with graceful sweeping arms that swirl outward like a cosmic pinwheel, spinning slowly through space. Others are more like enormous, smooth spheres floating through the darkness. These are called elliptical galaxies, and they typically contain older, more mature stars that have been shining for billions of years. Then there are irregular galaxies, which don't follow any clear or predictable pattern. These fascinating structures often acquired their strange, twisted forms because they crashed into other galaxies sometime in their tumultuous past. These cosmic collisions reshaped them into the unique asymmetrical forms we observe today. Galaxies aren't simply floating around randomly in the endless void of space. They serve as the fundamental building blocks of the entire universe. Inside these vast stellar cities, new stars are continuously being born, shining brilliantly for millions or even billions of years, and then eventually dying, sometimes in spectacular explosive endings. These dramatic stellar deaths help shape what each galaxy ultimately becomes over cosmic time. Galaxies are also the cosmic neighborhoods where planets like our Earth are found. They contain everything we know and can observe: asteroids tumbling through space, comets tracing their elliptical paths, planets of all sizes, countless stars, and that mysterious dark matter too. The diversity within galaxies is truly astounding when you consider the vast range of cosmic phenomena they contain. Galaxies can vary dramatically in size and complexity. Some are relatively small and contain only a few billion stars scattered throughout their structures. Others are absolutely enormous, containing hundreds of billions or even trillions of stars packed into their vast reaches. Our Milky Way falls somewhere in the middle of this range, hosting approximately 200 billion stars within its spiral arms and central bulge. The universe is absolutely filled with galaxies stretching in every direction we look. There are billions upon billions of them that we can detect with our most powerful instruments. Each one has its own unique story to tell, providing us with valuable clues about how the universe was born and how it has changed, evolved, and matured over the vast spans of cosmic time. Whether large or small, simple or complex, every single galaxy plays an important role in the universe's grand evolutionary story. Scientists believe that galaxies first started forming a few 100 million years after the Big Bang, which was the extraordinary event that began everything we know in the universe. The Big Bang occurred approximately 13.8 billion years ago, marking the moment when space, time, matter, and energy all came into existence. Back in those earliest times, the universe was incredibly young and unimaginably hot, filled with intense energy and radiation. During that primordial era, the only chemical elements that existed anywhere were hydrogen and helium, the two simplest and lightest elements on the periodic table. As cosmic time gradually passed and the universe continued, expanding and cooling, gravity began its patient work of pulling together enormous clouds of these primordial gases and cosmic dust. These massive clouds eventually collapsed under their own immense weight, leading to the birth of the very first stars that had ever shone in the cosmic darkness. These newly born stars then slowly gathered together under gravity's influence to form the first galaxies. However, these early galactic structures were quite different from the mature, well-organized galaxies we observe in today's night sky. They were much smaller, less complex in their structure, and composed primarily of young, hot, glowing stars that burned with intense brightness. These primitive early galaxies didn't yet contain the heavier chemical elements like carbon, oxygen, or iron that we find abundantly in modern stellar systems. But despite their simplicity, these early galactic pioneers helped lay the foundation for building the larger, more intricate and chemically diverse galaxies we see scattered throughout our present-day universe. Since that moment of the Big Bang, our universe has been continuously expanding in all directions. Galaxies have been slowly drifting apart from each other as space itself stretches, and this cosmic expansion hasn't slowed down or stopped. In fact, astronomers have discovered that the expansion is actually accelerating, getting faster over time, a phenomenon that scientists are still working to fully understand and explain. As galaxies moved through space and gradually grew larger over billions of years, they sometimes encountered each other and merged together in spectacular cosmic collisions. These galactic mergers and interactions helped create many of the large, beautiful, and complex galactic structures we observe throughout the universe today. But recently, the James Webb Space Telescope, often affectionately called JWST by astronomers, has made discoveries that have completely surprised and amazed the entire scientific community. It has found galaxies that formed much earlier in cosmic history than scientists ever thought was theoretically possible. This groundbreaking research has fundamentally changed how we understand and think about how the early universe developed and evolved. One of the most surprising things that JWST has discovered is the existence of galaxies that are far older than anyone had previously expected or predicted. For many years, scientists had confidently believed that the first galaxies didn't appear in the universe until around 400 to 500 million years after the Big Bang occurred. This theoretical timeline was based on careful calculations, suggesting that the universe needed sufficient time to cool down adequately so that stable stars could begin forming from the primordial gas clouds. However, JWST has discovered galaxies that may have formed just a few 100 million years after the Big Bang, much earlier than any previous models had suggested was possible. Even more, surprising and puzzling, these incredibly ancient galaxies appear remarkably well-formed and densely packed with mature stars. This means they must have assembled very quickly, far faster than scientists ever imagined was theoretically possible, given the conditions of the early universe. This revolutionary discovery is forcing scientists to completely rethink and reconsider how rapidly the universe changed and evolved after its initial creation. The implications of finding such mature galactic structures so early in cosmic history challenges many of our fundamental assumptions about the pace of cosmic evolution. One especially remarkable discovery involved a galaxy that appears to have formed just 230 million years after the Big Bang, an almost impossibly early time in the universe's development. This finding goes against nearly everything scientists previously believed about how galaxies begin their formation process and gradually grow over time. For such a sophisticated galactic structure to form so incredibly early, the physical conditions in the universe must have been dramatically different from what researchers had theorized. This discovery strongly hints that something previously unknown and unexpected, perhaps related to how matter initially clumped together or how the very first generation of stars were born, was happening during those crucial early epochs of cosmic history. These findings are extremely important because they demonstrate that many of our past theoretical ideas and models about the universe's development might need significant revision, or might even be fundamentally incorrect. The surprisingly rapid creation and evolution of these ancient galaxies challenges the long-held scientific belief that galaxy formation was necessarily a slow, gradual process that required billions of years to complete. Now scientists are actively wondering what might have been special or unique about the conditions in the early universe. Was there something unusual occurring that somehow helped galaxies form, and mature so quickly? Could there have been exotic types of dark matter interactions or unknown chemical processes that we don't yet understand or haven't discovered? These are the kinds of fundamental questions that JWST's discoveries are raising, forcing us to reconsider our basic understanding of cosmic evolution. JWST has also revealed that these incredibly ancient galaxies were bustling with activity and stellar formation. They were creating new stars at remarkably fast rates, far exceeding what theoretical models had predicted was possible. Scientists had previously assumed that star formation in the early universe would be relatively slow and inefficient because there weren't sufficient quantities of heavy elements like carbon or oxygen available, elements that are typically needed to facilitate efficient star formation processes. These heavier elements are normally produced inside older, more mature stars through nuclear fusion, processes then dispersed into space when those stars die. But if these ancient galaxies were already creating vast numbers of stars at such early times, then perhaps the conditions for star formation were much more favorable than we had previously understood. Alternatively, maybe our fundamental understanding of how the first generation of stars formed and evolved is completely wrong and needs to be reconsidered from the ground up. Some of the galaxies that JWST has observed are also much larger and more structurally complex than anyone had expected for such young cosmic objects. They display organized shapes, clear structural features, and contain a diverse variety of different types of stars within their boundaries, all of which is very surprising considering how incredibly young these galactic systems are in cosmic terms. Scientists had long believed that galaxies in the early universe would necessarily be small, simple, and relatively unorganized. But these groundbreaking discoveries prove otherwise and challenge many of our basic assumptions about early cosmic evolution. These surprising findings also raise entirely new questions about the roles of dark matter and dark energy in the early universe. These two mysterious and invisible components make up the vast majority of the universe's total mass and energy content, but we still don't understand their fundamental nature or how they interact with normal matter. The new discoveries suggest that dark matter might have played a much larger and more influential role in the formation and evolution of early galaxies than we had previously theorized. Similarly, dark energy might be affecting the rate at which the universe expands in ways that we don't yet understand or haven't properly accounted for in our theoretical models. All of these unexpected and paradigm-shifting discoveries made by the James Webb Space Telescope may completely revolutionize how scientists explain and understand the early history and evolution of our universe. It's now becoming clear that many of our older theoretical ideas about the universe's beginning, development, and growth are incomplete at best, and may need major revisions or complete replacement. Scientists will need to develop entirely new theories and models to explain how these ancient galaxies could have formed and matured so quickly during the universe's infancy. These new findings will likely lead to major theoretical breakthroughs and paradigm shifts in the coming years. Scientists will probably need to fundamentally rethink everything from how the very first stars were born to how galaxies grow, evolve, and interact with each other over cosmic time. These discoveries also show us that the first few 100 million years after the Big Bang, an era that we still know relatively little about, could be absolutely full of secrets and surprises waiting to be uncovered by future observations. This surprising and revolutionary discovery raises many profound, new questions about the very beginning of everything we know and observe. Scientists are still working diligently to fully understand what all of these findings mean for our understanding of cosmic evolution. But one thing is becoming increasingly clear. The universe is far more mysterious, complex, and amazing than we ever dared to imagine. One of the most absolutely jaw-dropping discoveries made by astronomers involves a galaxy known as GNZ11. This ancient galactic structure is located an almost incomprehensible 13.4 billion light-years away from our Earth. In other words, when we observe it through our most powerful telescopes, we're seeing it exactly as it appeared just 400 million years after the Big Bang occurred, an incredibly early time in the universe's development. Most galaxies simply wouldn't have had sufficient time to grow significantly by that early epoch in cosmic history. But GNZ11 is completely different and defies all expectations. What makes GNZ 11 so absolutely surprising and theoretically challenging is its enormous size and mature structure. For such a young galaxy existing so early in cosmic history, it's far bigger and more complex than anyone had expected or predicted was possible. It contains hundreds of billions of stars within its boundaries, putting it in the same size category as our own Milky Way galaxy, which is more than 13 billion years old and has had all that vast amount of time to slowly grow, evolve and mature through cosmic processes. Yet somehow, this cosmic infant was already gigantic and well-structured when the universe itself was still in its earliest infancy. Even more incredible and puzzling is how rapidly GNZ 11 appeared to grow and develop. Not only was it remarkably large for its age, but it was also expanding and evolving at a speed that completely stunned the scientific community. Galaxies at that early stage in the universe's development weren't supposed to grow and mature this quickly, according to all existing theoretical models. This means that GNZ 11 somehow had access to enormous quantities of gas, the primary raw material needed for creating new stars, at a time when such abundant resources were thought to be extremely scarce throughout the early universe. This discovery has forced scientists to completely rethink and revise their fundamental ideas about how galaxies form, grow, and evolve over cosmic time. GNZ 11 simply doesn't fit into any of the older theoretical models and challenges our basic understanding of early cosmic evolution. And GNZ 11 isn't alone in defying our expectations. Scientists have now discovered numerous other massive mature galaxies that existed during the early universe, and they're all equally puzzling and theoretically challenging. These ancient galactic structures are located millions or even billions of light years away from us, scattered throughout the observable cosmos. And they're not only enormous in size, but also remarkably complex in their internal structure and organization. Some of these early galaxies already possess beautiful spiral arms or other detailed architectural features that we typically associate with much older, more mature galactic systems. Others even contain supermassive black holes sitting at their very centers, the kind of exotic objects we expected to find only in fully mature galaxies that had billions of years to develop and evolve. That's like discovering a fully grown adult in a nursery filled with newborns. It simply doesn't match anything we thought we understood about cosmic development and evolution. The fundamental question that now puzzles astronomers is, how could these galaxies grow so incredibly fast and become so structurally complex when the universe was just beginning its existence? One intriguing idea that scientists are actively exploring is something called direct collapse. Normally, galaxies are thought to grow slowly and gradually over vast periods of time. Tiny clouds of primordial gas slowly come together under gravity's influence, gradually forming stars and building up a galactic structure piece by piece over billions of years. But with direct collapse, everything happens much more rapidly and dramatically. A giant cloud of gas can collapse all at once under its own gravity, forming an entire galaxy in a much shorter time frame than traditional models suggest. This rapid formation process could potentially explain why we're observing these giant, mature galaxies so early in cosmic history, long before traditional models suggest they should have had time to develop. Another fascinating possibility is that the early universe was simply fundamentally different from what we see today, more extreme, more chaotic, and filled with much more energy and activity than we had previously imagined. In the first few 100 million years following the Big Bang, space might have been filled with incredibly thick clouds of gas, intense radiation, and enormous amounts of violent cosmic activity. This wild, turbulent environment might have pushed gas into extremely dense pockets, where it could quickly and efficiently transform into stars. Galaxies could have formed rapidly in this cosmic chaos, developing much faster than they do in today's more stable and organized universe. The conditions were so different that normal rules and timescales simply didn't apply. Scientists also believe that the mysterious substance called dark matter may have played a crucial and previously underestimated role in these processes. Dark matter is an invisible, mysterious substance that doesn't emit any light or energy that we can directly detect, but it does exert gravitational influence on everything around it. This means it can pull and attract normal matter, gas, and stars toward concentrations of itself. If dark matter was clustered in certain regions of the early universe, it could have gravitationally pulled in enough material to help galaxies form very quickly and grow much larger than anyone had expected was theoretically possible. The gravitational scaffolding provided by dark matter might have been the key to rapid galaxy formation in the early cosmos. Another absolutely mind-blowing discovery is that some of these incredibly ancient galaxies already contained supermassive black holes at their centers. These cosmic monsters are millions or even billions of times more massive than our own Sun. Normally, black holes are thought to require billions of years to form and grow, starting from the collapsed cores of massive stars and gradually accumulating more matter over vast periods of time. But here we are finding these gigantic black holes in galaxies that were only a few 100 million years old, far too young for traditional black hole formation and growth processes to account for their enormous sizes. How could they have grown so massive so quickly? This is one of the most puzzling questions in modern astrophysics. One possible explanation involves the same direct collapse process that might explain rapid galaxy formation. Maybe enormous gas clouds in the early universe didn't even bother going through the normal process of first forming stars. Instead, they might have collapsed directly into black holes, skipping the usual intermediate steps and allowing these cosmic giants to form much faster than traditional models suggest. Another intriguing idea is that these black holes were engaged in incredibly rapid feeding frenzies, consuming enormous amounts of gas and matter from their surroundings, and growing exponentially by pulling in everything nearby. This cosmic buffet could potentially explain why they managed to become so massive in such a relatively short period of cosmic time. These revolutionary discoveries have turned many old theoretical frameworks completely upside down. For decades, astronomers confidently believed that galaxies formed slowly and gradually, with stars slowly gathering together under gravity's patient influence over billions of years. But now, with clear evidence of rapidly forming, enormous galaxies and supermassive black holes appearing so early in cosmic history, scientists are exploring entirely new theoretical possibilities. Maybe galaxy formation didn't follow just one predictable path throughout cosmic history. Perhaps some galaxies grew slowly and gradually as we had previously thought, while others exploded into existence almost overnight in spectacular bursts of cosmic creativity. This new perspective opens up absolutely fascinating possibilities for understanding cosmic evolution. It suggests that the early universe wasn't the quiet, simple, slowly evolving place we had imagined. Instead, it might have been an incredibly wild and energetic time, filled with rapid changes, dramatic transformations, and explosive growth. Galaxies could have grown, merged, collided, and transformed in a matter of millions rather than billions of years. These discoveries also raise profound new questions that challenge our fundamental understanding of cosmic evolution. Could dark matter have shaped and influenced the early universe even more dramatically than we had previously theorized? Could supermassive black holes have influenced how galaxies formed from the very beginning of cosmic time, rather than being late additions to mature galactic systems? It's starting to look like these forces and processes, once considered minor side characters in the cosmic story, might have actually played leading roles in shaping the very structure and evolution of our universe from its earliest moments. Most amazingly, these findings might even require us to completely rewrite our understanding of cosmic history and the timeline of universal development. If galaxies could form so rapidly and grow so enormous right after the Big Bang, then the early universe might have evolved much more quickly and dramatically than anyone had previously imagined possible. This could fundamentally change how we understand the so-called cosmic dark ages, that mysterious period after the Big Bang when the universe was thought to be dark, empty, and relatively quiet. Maybe those early eons weren't so peaceful and uneventful after all. Perhaps they represented a time of blazing stars, rapidly growing galaxies, and violent supermassive black holes, an age of spectacular cosmic fireworks and dramatic transformations instead of the silent, gradual development we had envisioned. Today, when we look out into the vast expanse of space with our most powerful telescopes, most of the galaxies we observe fall into two main categories: spiral and elliptical. Spiral galaxies, such as our own beautiful Milky Way, are easily recognizable because they resemble giant cosmic pinwheels slowly spinning through space. Their long, graceful arms swirl outward from a bright, dense central core, and these spiral arms are filled with countless stars, vast clouds of gas, and cosmic dust, all rotating together in an elegant celestial dance that has continued for billions of years. Elliptical galaxies, on the other hand, don't possess these distinctive spiral arms. Instead, they appear round or oval-shaped when viewed through telescopes, and their constituent stars move in many different directions throughout the galactic structure, creating a smoother, more uniform appearance than their spiral cousins. These elliptical systems often contain older, more mature stars that have been shining steadily for billions of years. But when scientists use advanced instruments to look deep into space and far back through cosmic time, they discover that the first galaxies that ever formed were dramatically different from the organized, mature galactic structures we observe in today's universe. These ancient galactic pioneers didn't have neat, predictable shapes or organized structures. Instead, they appeared messy, unbalanced, and chaotic, often resembling strange, irregular blobs scattered. Throughout the early cosmos, it was as if the universe had not yet learned or figured out how to create galaxies with orderly, symmetrical appearances. Instead, everything seemed to be in constant motion, swirling, crashing, merging, and shifting in what appeared to be perpetual cosmic confusion and turmoil. The early universe was a much more chaotic and unpredictable place than the relatively organized cosmos we see today. This dramatic difference in galactic appearance and structure has everything to do with how these ancient systems were born and evolved. In the early days of cosmic history, just a few 100 million years after the Big Bang occurred, approximately 13.8 billion years ago, galaxies were still incredibly young in cosmic terms. They were much smaller in size and hadn't yet had sufficient time to develop into the neat spiral patterns or smooth elliptical shapes that characterize mature galactic systems. The stars, cosmic dust, and gas clouds that compose these early galaxies were scattered in irregular clumps and concentrations, often appearing as if they were still in the process of being gravitationally pulled together by invisible forces. These early galactic structures were essentially still under construction, and the universe surrounding them remained wild, unsettled, and filled with dramatic activity. During those primordial times, space itself was filled with intense energy, radiation, and cosmic chaos. Galaxies existed much closer together than they do today, and they frequently encountered each other in spectacular cosmic collisions and mergers. When these galactic crashes occurred, their shapes became even more twisted, distorted, and strange-looking than they already were. It wasn't until much later in cosmic history, after billions of years of gradual evolution, merging, and gravitational settling, that many galaxies finally began to take on the familiar, organized shapes and structures we recognize and study today. The transformation from chaotic early galaxies to organized mature systems was a slow process that required enormous amounts of time and countless gravitational interactions. Scientists had previously assumed that as galaxies aged and matured over cosmic time, they would naturally and inevitably become more organized, structured, and symmetrical in their appearance. However, when they began studying the earliest galaxies that formed shortly after the Big Bang, they were genuinely surprised by what they discovered. These ancient galactic systems weren't neat, smooth, or well-organized at all. Instead, they appeared irregular, lumpy, and chaotic, like cosmic puzzle pieces that hadn't yet figured out how to fit together properly. Some of these early galaxies looked like broken shards of celestial material scattered through space, while others appeared to be composed of multiple smaller galactic fragments that hadn't finished merging into a single, coherent structure. It was truly a time of cosmic chaos and upheaval when gravity was still working patiently to bring some semblance of order and organization to the universe. The early cosmos was a much more turbulent and unpredictable place than the relatively stable universe we observe today. But you might wonder, how exactly do astronomers know what these incredibly ancient galaxies looked like, especially since they're located so unimaginably far away and formed such a long time ago? The answer lies in understanding the fundamental nature and behavior of light itself. Light doesn't travel instantaneously from one place to another. It takes time to move through the vast emptiness of space. The farther away a cosmic object is located, the longer its light takes to complete the journey and reach our telescopes here on Earth. So, when we observe galaxies that are billions of light years distant from us, we are actually seeing them exactly as they appeared billions of years ago, not as they exist today. It's like having access to a natural time machine built from light itself. For example, if a galaxy is located 1 billion light-years away from Earth, then the light we currently observe from that galaxy actually left its source 1 billion years ago. This means we're seeing that galactic system as it existed in the distant past, not in its present state. The farther out into space we look with our instruments, the further back through cosmic time we're able to peer. This is precisely how scientists study and learn about the early universe. They don't need to physically travel to distant locations or somehow journey back through time. Instead, they capture and analyze the ancient light that has been making its slow journey toward us for billions of years, carrying with it information about cosmic conditions in the distant past. To accomplish this remarkable feat of cosmic archaeology, astronomers employ some of the most sophisticated and powerful scientific instruments ever constructed by human civilization. The Hubble Space Telescope, which was launched in 1990, has spent decades capturing breathtaking images of galaxies located incredibly far away, providing us with unprecedented views of cosmic structures across vast distances and time periods. But an even more powerful and advanced tool arrived in 2021, the James Webb Space Telescope. This revolutionary instrument represents the pinnacle of human engineering and scientific ambition. The James Webb Space Telescope, affectionately known as JWST by astronomers, was specifically designed and built to study the earliest and most distant galaxies in the observable universe. It possesses the remarkable ability to detect and analyze infrared light, which is absolutely perfect for observing ancient galaxies whose light has traveled so far through expanding space that it has been stretched from visible wavelengths into the infrared portion of the electromagnetic spectrum. Thanks to this specialized capability, JWST can capture sharper, clearer, and more detailed images of galaxies from the very beginning of cosmic time than any instrument that came before it. And what this incredible telescope reveals is absolutely astonishing and often surprising. Many of these ancient galactic structures appear far messier, more irregular, and more chaotic than scientists had expected based on theoretical models. This surprising discovery has forced astronomers to fundamentally rethink their ideas about how galaxies originally formed and evolved during the universe's earliest epochs. One of the most fascinating clues to understanding this cosmic puzzle comes from studying something that remains completely invisible to our eyes, but is incredibly powerful in its influence on galactic formation and evolution. Dark matter remains one of the universe's most enchanting mysteries. This invisible substance comprises approximately 27% of all the mass and energy that exists throughout the cosmos. We cannot see it with our eyes or touch it with our hands because it doesn't emit light or heat the way stars and planets do. Yet we know with certainty that it exists because its gravitational influence pulls on everything around it, shaping the very structure of our universe. In the early universe, dark matter didn't spread out uniformly across space like a gentle mist. Instead, it formed dense concentrations in certain regions, creating invisible knots and clusters scattered throughout the cosmic void. These gravitational anchors pulled in enormous clouds of primordial gas and cosmic dust. Over vast periods of time, this material gradually gathered and collapsed under its own gravitational weight, igniting nuclear fusion and creating the first stars, which eventually organized themselves into the earliest galaxies. Because the dark matter was distributed so unevenly throughout space, the galaxies that formed around these invisible scaffolds were also irregular and asymmetrical, displaying twisted shapes and chaotic structures. This fundamental unevenness explains why so many of the ancient galaxies we observe appear so disorganized and messy compared to the elegant spiral and elliptical galaxies we see in today's more mature universe. Another significant reason for the irregular shapes of these early galactic systems is that they existed much closer to one another than galaxies do today. The universe was far more crowded during those ancient times, with cosmic neighborhoods packed tightly together. Small proto-galaxies drifted near each other and frequently crashed together in spectacular cosmic collisions that reshaped their structures entirely. These galactic mergers didn't usually result in individual stars actually hitting each other directly. Stars are spaced so incredibly far apart that even during galactic collisions, they rarely make contact with one another. However, the vast clouds of gas and dust that filled the space between stars would slam together with tremendous force, heating up dramatically and triggering intense bursts of new star formation throughout the merging systems. These violent cosmic encounters fundamentally changed the shape and behavior of galaxies, making them even more chaotic and irregular than they already were. As cosmic time progressed, these smaller galactic fragments gradually joined together to form increasingly larger and more complex structures. These cosmic collisions played an absolutely crucial role in shaping the diverse array of galaxies we observe throughout today's universe. Even in our current era, galaxies still occasionally collide and merge with one another. However, during the early universe, these dramatic encounters happened much more frequently because galactic systems were positioned much closer together in the smaller, denser cosmos. These early cosmic smash-ups represented a major driving force in galactic evolution and development. The early universe also contained vastly more free-floating gas than we observe today, particularly hydrogen and helium, the lightest and most abundant chemical elements. This primordial gas acted like premium fuel for star formation processes. Because there were such enormous quantities of this raw material available, galaxies could manufacture new stars rapidly and in virtually any location, not just in neat, orderly patterns. This abundance of star-forming material explains why early galaxies appear so scattered and disorganized when we observe them through our most powerful telescopes. In today's mature galaxies, star formation tends to occur in calm, well-regulated regions, such as the graceful spiral arms of galaxies like our own Milky Way. But billions of years ago, stellar birth was wild and completely unpredictable. New stars could appear almost anywhere within a galactic system, and they often formed in dramatic bursts of activity, especially following galactic mergers and collisions. This chaotic pattern of stellar formation made early galaxies appear even more uneven, lumpy and irregular than the organized systems we're familiar with today. Another enormously influential player in this cosmic story involves something truly extraordinary: supermassive black holes. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These are truly mind-boggling cosmic objects with gravitational fields so incredibly strong that nothing, not even light itself, can escape once it crosses too close to their event horizons. But these cosmic giants don't simply sit quietly at galactic centers doing nothing. They actively shape their host galaxies in remarkable and profound ways. Scientists now believe that even in the very early universe, supermassive black holes had already begun forming and exerting their influence on surrounding cosmic structures. Their tremendously powerful gravitational attraction pulled in nearby gas clouds, cosmic dust, and sometimes even entire stellar systems. This constant feeding activity may have made young galaxies even more turbulent and chaotic, preventing them from settling into nice, organized shapes and structures. What makes this even more fascinating is that when material falls into a black hole, it heats up to incredible temperatures and releases absolutely massive amounts of energy, sometimes generating more energy output than all the stars in an entire galaxy combined. Some supermassive black holes even launch powerful jets of highly energetic particles at nearly the speed of light. These dramatic outbursts can blast through space across vast distances, rearranging gas and dust throughout their host galaxies, and fundamentally changing how and where new stars are born. In this way, supermassive black holes may have played a crucial role in shaping the wild, uneven appearance of early galactic systems. Even today, scientists are still working diligently to understand just how important supermassive black holes were in shaping the overall structure and evolution of our universe. But one thing has become increasingly certain: they were not merely passive bystanders in cosmic evolution. Instead, they were active, dramatic players in the grand story of galaxy formation and development. As billions of years gradually passed, our universe slowly settled down and became more stable. Galaxies grew larger and more massive, eventually settling into the more organized shapes and developing the beautiful spiral arms and smooth elliptical forms we admire throughout today's cosmos. But by looking deep into space and peering far back through cosmic time, astronomers can still witness the universe's chaotic childhood, a time when galaxies were wild, energetic, and absolutely bursting with creative possibility. For billions upon billions of years, a powerful and completely invisible force has been steadily shaping the universe around us. Gravity, this gentle but utterly unrelenting attraction, has acted like a cosmic sculptor, slowly and patiently changing the way galaxies look and behave throughout cosmic history. Gravity doesn't just keep stars and planets locked in their orbital paths. It also brings entire galaxies together across vast cosmic distances. Sometimes two or more galactic systems drift so close to each other that they actually collide and merge in spectacular slow-motion events that unfold over millions of years. When galaxies crash into one another, the individual stars within them don't usually collide directly with each other. This is because stars are separated by such enormous distances that each one is like a tiny speck floating in a vast ocean of mostly empty space. But even though the stars themselves rarely make contact, their galaxies' combined gravitational forces create tremendous turbulence in the massive clouds of gas and dust that fill the space between stellar systems. This cosmic stirring causes new stars to be born in great waves of activity, like brilliant fireworks lighting up the night sky across multiple galactic regions simultaneously. At first, these galactic collisions create wild, chaotic shapes, twisting, stretching, and bending the participating galaxies into strange and unusual forms that bear no resemblance to their original structures. But, as cosmic time continues to pass, things gradually begin to calm down and stabilize. The newly merged galactic system starts to settle into a more peaceful and orderly configuration. Some of these post-collision galaxies develop beautiful spiral arms similar to our own Milky Way galaxy, while others become smooth and round, transforming into the elegant elliptical galaxies we observe scattered throughout the universe. This ongoing story of galactic evolution is still unfolding around us even today. The universe is not finished growing and changing. Galaxies continue merging with each other, and their shapes and structures continue to evolve in response to gravitational interactions and cosmic processes. One of the most amazing examples of ongoing galactic evolution is happening right here in our own cosmic neighborhood. The Milky Way galaxy is slowly but steadily moving toward its nearest major neighbor, the Andromeda Galaxy. These two galactic giants are currently on a collision course, and in approximately 4 billion years from now, they will come together in a breathtaking merger event. Eventually, after this cosmic dance concludes, they will combine to form a single, much larger galactic system. This demonstrates clearly that the grand dance of the galaxies is far from finished. Our universe remains full of movement, transformation, and ongoing evolution. In recent years, astronomers have made a truly surprising discovery about the galaxies that existed during the very earliest epochs of cosmic history. These ancient galactic systems were far more chaotic and disorderly than anyone had previously expected or predicted. This finding has completely revolutionized the way scientists think about how galaxies originally form and develop over time. For many decades, researchers believed that galaxies slowly and gradually grew into neat, organized shapes over vast periods of cosmic time. But now we understand that the earliest galaxies were wild, irregular, and completely unpredictable in their structure and behavior. These strange and unusual shapes tell us that the early universe, existing just a few 100 million years after the Big Bang occurred, was a much more energetic and unstable environment than we had previously imagined. The exact forces and processes that shaped those first galactic systems remain largely mysterious to us. Scientists are still working hard to understand what caused them to look and behave the way they did. This cosmic puzzle represents one of the most exciting challenges in contemporary astronomy. We can think of these early galaxies as the fundamental building blocks of our universe. By carefully studying their properties and behavior, scientists are slowly piecing together the long and incredibly complicated history of how galaxies came to exist in their current forms. These detailed observations help us understand how the universe transformed from a wild, stormy place filled with raw energy and chaos into the vast, structured cosmos we observe today, complete with its graceful spiral galaxies and massive clusters of organized galactic systems. The odd and unusual forms of these early galaxies serve as clues in a cosmic detective story of epic proportions. They show us how galaxies are born from primordial materials, how they crash into each other in spectacular collisions, and how they gradually transform over billions of years of cosmic evolution. As our technology continues to improve, and we develop increasingly powerful telescopes and observational instruments, we'll gain the ability to look even deeper into space and further back through cosmic time. This means we will likely discover even more secrets about how our universe originally began and evolved into its current state. Right now, scientists feel like they're just at the very beginning of this incredible journey of discovery. Each new observation and breakthrough brings us a little bit closer to understanding our universe's mysterious past and the fundamental processes that shaped everything we see around us today. One of the most exciting and awe-inspiring discoveries in modern astronomy involves something scientists call the earliest light. This ancient radiation comes from some of the very first galaxies that formed anywhere in the universe, galactic systems that came into existence only 200 to 300 million years after the Big Bang occurred. In cosmic terms, that represents just brief moments after our universe began its existence. This incredibly ancient light provides us with a rare and powerful glimpse into the universe's mysterious and largely unknown past, offering views of a time when the first stars were being born and beginning to illuminate the darkness of the early cosmos with their brilliant nuclear fires. In the very beginning, immediately following the Big Bang, our universe was not filled with the stars and galaxies we observe today. Instead, it was permeated by a hot, dense fog composed of countless tiny particles. These particles existed everywhere throughout space, and they prevented light from moving freely through the cosmic medium. The particles of light, which scientists call photons, kept bouncing around chaotically, scattered in all directions by this thick cloud of matter that filled all of space. The situation was similar to trying to shine a flashlight through extremely dense fog. You could turn the light on, but the illumination wouldn't travel very far before becoming scattered and absorbed. It took hundreds of thousands of years for our universe to cool down and expand sufficiently so that this primordial fog could finally clear. Eventually, the particles began combining together to form the first atoms, and light was no longer trapped and scattered. For the first time, electromagnetic radiation could move freely through the vast expanses of space. This moment represents one of the most important transitions in all of cosmic history. It marks the birth of what we now call the cosmic microwave background, or CMB, a faint glow of ancient radiation that still permeates the entire universe to this very day, carrying information about the early cosmos. This ancient background radiation has been traveling across space for over 13 billion years, and when we detect and study it today, we are truly looking backward through time to observe the universe as it existed in its earliest epochs. But there's something even more remarkable than the cosmic microwave background. The light from the first galaxies, which appeared approximately 200 to 300 million years after the Big Bang, represents something truly special and unprecedented. This starlight was among the very first illumination to shine anywhere in the universe, marking a fundamental turning point in cosmic evolution, a transformation from a dark, foggy cosmos into one filled with glowing stars and organized galactic systems. Before this crucial period, our universe resembled a shadowy sea of primordial gas floating in darkness. But when those first stars finally ignited their nuclear furnaces, their brilliant light began pushing away the cosmic darkness, clearing the remaining fog and filling space with soft, brilliant illumination for the first time in cosmic history. This extraordinary moment is known as the cosmic dawn, the time when the first light broke through the primordial shadows and began the process of cosmic illumination that continues today. What makes this discovery so scientifically important is that astronomers have now successfully detected some of this incredibly ancient light using our most advanced telescopes and instruments. This means we are actually observing light that began its journey across space over 13 billion years ago, long before our own Milky Way galaxy, our solar system, or our planet Earth even existed. This ancient light holds precious secrets and clues about how everything we know and observe today originally came to be. It carries information about the earliest processes of star formation, galaxy assembly, and cosmic evolution that shaped our universe into its current form. The era of cosmic dawn is incredibly important for understanding how our universe developed, from its initial state into the complex structured cosmos we observe today. After the Big Bang, our universe was extremely hot and chaotic, filled with intense energy and radiation. Over vast periods of time, it slowly expanded and cooled down, allowing matter to condense and organize itself. Eventually, tiny particles came together under gravity's influence to form the first stars, and these stars gradually joined together to create the first galaxies. These early galactic systems would go on to shape the entire large-scale structure of our universe over billions of years of cosmic evolution. But actually proving when and how this fundamental transformation occurred represented a huge challenge for astronomers. The primary difficulty was the enormous distances involved. The farther away a galaxy is located, the longer its light takes to reach our telescopes here on Earth. So if a galaxy formed billions of years ago, its light has had to travel for billions of years before we can finally observe it. By the time this ancient light reaches us, it has become extremely faint and difficult to detect. Not only is it incredibly dim, but it has also been stretched out as our universe itself continues to expand. This stretching effect causes the light to shift into the infrared portion of the electromagnetic spectrum, which is completely invisible to human eyes. To detect this stretched, ancient light, scientists needed incredibly powerful and sophisticated instruments. They relied on advanced technology, including the revolutionary James Webb Space Telescope, the long-serving Hubble Space Telescope, and massive ground-based telescopes specifically designed to detect infrared radiation. These remarkable instruments are engineered to pick up signals that our eyes could never perceive directly. Thanks to this cutting-edge technology, scientists have gained the ability to peer far into space and successfully spot galaxies from the universe's earliest days. It's like using a natural time machine to observe what our universe looked like over 13 billion years ago, when it was still in its cosmic infancy. One of the biggest breakthroughs in this field came with the launch of the James Webb Space Telescope, which was specially designed and built to detect infrared light with unprecedented sensitivity and resolution. This remarkable instrument allows scientists to see further into space and observe ancient cosmic structures more clearly than ever before. Without telescopes like JWST, we wouldn't be able to detect the incredibly faint glow emanating from those ancient galactic systems. The collaboration between space-based telescopes and ground-based observatories has been absolutely essential for uncovering the story of our early universe and its evolution. This ancient light doesn't just tell us when the first galaxies formed, it also reveals how quickly our universe began creating organized structure after the Big Bang occurred. To everyone's surprise, galaxies and stars started forming much earlier than many scientists had predicted, based on theoretical models. This discovery fundamentally changes how we think about the early universe and how rapidly it evolved from primordial chaos into organized cosmic structure. Even more fascinating is what this ancient light reveals about the very first stars, known as population 3 stars. These stellar pioneers were completely unlike any stars we observe in today's universe. They were composed almost entirely of hydrogen and helium, the two simplest chemical elements created during the Big Bang itself. These primordial stars contained virtually no heavier elements, what astronomers call metals, and because of this unique composition, they burned much hotter than modern stars, lived significantly shorter lives, and died in tremendously powerful explosive events. These first-generation stars helped transform the early universe by releasing enormous amounts of energy into their surroundings. This energy began the process of reionizing the gas that filled the cosmos, converting it from a neutral fog into a clear, glowing expanse where light could travel freely across vast distances. The first galaxies that formed from these early stellar populations were probably quite small and irregular in shape. Over cosmic time, they crashed into each other, merged together, and gradually grew larger and more complex. This slow process of galactic merging helped create the massive spiral and elliptical galaxies we observe throughout today's universe. By studying the properties of those tiny ancient galaxies, scientists are learning how galactic systems grow, evolve, and change over billions of years of cosmic time. This ancient light also connects us to two of the most mysterious and enigmatic forces in our universe: dark matter and dark energy. These invisible components make up the vast majority of the universe's mass and energy content, but we cannot see or directly touch them. We know dark matter must exist because of its powerful gravitational influence, which helps galaxies form and remain gravitationally bound together. We believe dark energy is responsible for the accelerating expansion of our universe over cosmic time. The light from the early universe provides us with valuable clues about how dark matter helped shape the first galaxies and influenced the way our universe grew and evolved from its initial state. As scientists continue to explore deeper into space and further back in time, they're uncovering even more ancient light, gradually building a clearer and more complete picture of our universe's beginning and early evolution. Every new piece of ancient light we discover adds another chapter to the grand story of how the cosmos came to be. It helps us understand how the first stars formed, how early galaxies evolved and merged, and how the magnificent large-scale structure of our universe gradually took shape over billions of years. What's even more amazing is that when we observe this ancient light, we are literally looking backward, through time itself. This radiation began its journey millions and billions of years ago, long before our Earth, our Sun, or even our galaxy existed in their current forms. So when we study this primordial light, we are witnessing the actual birth and early development of our universe. It's like watching an ancient movie that's still playing out across the cosmic sky, showing us in vivid detail how everything began and evolved. The discovery of galaxies that formed only 200 to 300 million years after the Big Bang represents just the beginning of an incredible journey into the deep past of our cosmic history. With newer and increasingly powerful telescopes currently being built and planned, scientists will gain the ability to look even further into space and uncover more secrets of the early cosmos. There are still countless mysteries left to solve and questions to answer. Each new discovery brings us closer to answering the biggest question of all. How did everything begin, and how did it evolve into the universe we know today? When we look toward the future, scientists around the world are filled with excitement and curiosity. They are eager to learn even more about the first galaxies that appeared in the early universe, the very first stars that ever shone, and the powerful events and processes that helped shape our universe into what it is today. These early cosmic times were filled with dramatic changes and transformations. By studying them carefully, we can begin to understand how our universe grew from something relatively simple into the enormous and incredibly complex place we now inhabit. One of the most important ways scientists study these early moments in cosmic history is by examining ancient light, radiation that was released billions of years ago from some of the oldest galaxies ever discovered by human technology. This light functions like a message from the distant past, carrying secrets that can help us understand where everything came from the shining stars we see each night in our sky to our own planet, and the life that flourishes here on Earth. It all connects back to the birth and early evolution of our universe. As we continue looking deeper into space with increasingly powerful instruments, we may even begin to understand the invisible forces that originally brought time, matter, and energy into existence at the moment of cosmic creation. One of the most exciting discoveries in modern astronomy is the successful detection of light from galaxies that formed only about 200 to 300 million years after the Big Bang occurred. Since the Big Bang happened approximately 13.8 billion years ago, this means scientists are observing galactic systems that were born when our universe was still in its cosmic infancy. This ancient light allows us to look backward through time itself, offering a rare and precious glimpse of our universe just after it began its existence. It's almost like examining a baby picture of the cosmos, showing us what everything looked like in its earliest stages. This discovery opens up incredible possibilities for scientific understanding. It helps researchers study how galaxies first formed from primordial materials, how the first stars were born and began shining, and how invisible forces like dark matter and dark energy influence the growth and evolution of cosmic structure. These discoveries also help us learn more about how our universe changed and transformed over vast periods of time, evolving from a hot, glowing fog into the star-filled sky we observe today. Thanks to amazing advances in technology, especially with powerful instruments like the James Webb Space Telescope, we now have the unprecedented ability to look farther into space than ever before in human history. This remarkable telescope functions like a giant time machine, helping us observe light that has been traveling across space for over 13 billion years. It allows us to explore the farthest and most ancient regions of our observable universe, revealing wonders that were once completely hidden and unknown to science. By studying this light from the distant past, scientists are gradually unlocking the secrets of how everything we observe today, stars, planets, galaxies, and even life itself, originally came to be through cosmic processes. Each new discovery brings us closer to understanding how our universe was formed, how it works and evolves, and what our place within it truly is. As we continue to explore deeper into space, we realize just how interconnected everything is, and how many more mysteries remain to be solved through future observations. The more we learn about our cosmic history, the more incredible and awe-inspiring the story of our universe becomes, and it's a story that continues unfolding around us every day. Right after the Big Bang occurred, our universe was an incredibly messy and superheated place, filled with rapidly moving matter and intense radiation. Everything was expanding quickly, and tiny variations in how matter was distributed throughout space began to become apparent. Some regions had more material squeezed into them than others, and this fundamental unevenness led to something absolutely amazing: the possible birth of the first black holes, known as primordial black holes. These black holes were completely different from the ones we usually hear about, those massive objects that form when huge stars run out of nuclear fuel and collapse catastrophically in on themselves. Primordial black holes may have emerged directly from the fabric of space itself during the universe's earliest moments. They didn't originate from dying stars like the black holes we observe today. Instead, they were created by the extreme conditions that existed in the very first moments after our universe began. During that time, space was not uniform everywhere. Some parts were denser with matter than others, and gravity began pulling these dense regions together. If a particular region became dense enough, it could crush itself under its own gravitational pull and form a black hole, even without requiring a star to collapse first. These early black holes could have formed just tiny fractions of a second after time itself began, making them some of the oldest objects in our universe, if any of them still exist today. Experts theorize that if enough of these very ancient black holes were created during the early universe, they could help explain the mysterious nature of dark matter, the strange, unseen substance that makes up most of our universe's mass, but doesn't interact with light or ordinary matter. Some of these primordial black holes might have evaporated over cosmic time through a process called Hawking radiation, which causes black holes to slowly lose mass by emitting particles. However, others, if they were large enough initially, might still be floating through space today, invisible to our telescopes. Though we cannot see them directly, they could still be affecting everything around them with their powerful gravitational influence, contributing to the cosmic web of dark matter that shapes large-scale cosmic structure. Experts believe that primordial black holes might have formed during the very first tiny moments after the Big Bang, when our universe was unbelievably hot and dense. In those initial microscopic fractions of a second, small but extremely compressed regions of space could have collapsed under their own immense gravitational pull, transforming into miniature black holes. These wouldn't have been like the supermassive black holes we now observe at the centers of galaxies today. Primordial black holes would have been incredibly tiny, perhaps no larger than a single proton or atomic nucleus, but despite their minuscule size, they could still contain enormous amounts of mass compressed into an unimaginably small space. Some experts theorize that their mass could have ranged from that of a small asteroid to a fraction of Earth's mass, all compressed into a space smaller than an atom. If any of these objects still exist today, these ancient black holes could be hiding somewhere in the vast expanses of our universe, undetectable by current technology. Some theoretical ideas even suggest they could constitute a significant portion of dark matter, the mysterious substance that makes up most of the mass in our universe, but cannot be observed with telescopes or detected through electromagnetic radiation. Proving that primordial black holes actually exist could help us unlock major secrets about the early universe and the fundamental laws that govern cosmic evolution, including our understanding of gravity and quantum mechanics on the smallest scales. In the first moments after the Big Bang occurred, our universe was superheated and incredibly compact, filled with a chaotic mixture of energy, intense radiation, and countless tiny particles. Unlike today's vast and well-organized universe, everything back then was compressed into a region of unimaginable heat and pressure. During those earliest times, matter was not distributed evenly throughout space. Some areas were slightly denser than others due to random quantum fluctuations that occurred during cosmic inflation. Most of the time, these tiny variations evened out as our universe expanded and cooled, but occasionally certain regions were so dense that they didn't disperse with the cosmic expansion. Instead, these overdense regions collapsed inward under their own gravitational attraction. This gravitational collapse led to what experts call primordial black holes, tiny but extremely dense objects that could have existed since the very beginning of cosmic time. Unlike the black holes that form from dying stars in today's universe, these primordial objects would have been created directly from the extreme conditions present during the first moments of cosmic existence, representing some of the most ancient structures that might still exist in our universe today. In the vast tapestry of cosmic history, there exist theoretical objects that challenge our understanding of the universe's earliest moments. These ancient black holes differ fundamentally from the stellar remnants we observe today, which typically form when massive stars exhaust their nuclear fuel and undergo gravitational collapse. Instead, these primordial objects emerged from the extreme conditions that characterize the infant universe. These theoretical black holes could range dramatically in size, from microscopic entities no larger than elementary particles, yet containing enormous mass, to larger structures that may have grown over cosmic time. If they persist in the modern universe, they could provide invaluable insights into the fundamental physics of the early cosmos and potentially solve the enduring mystery of dark matter's true nature. Scientists refer to these objects as primordial because they theoretically originated during the universe's first instance, long before stellar formation began. Unlike contemporary black holes that result from stellar death, these ancient entities would have materialized within seconds or minutes of the Big Bang. During this brief but extraordinary epoch, the universe existed as an incredibly dense and energetic plasma of fundamental particles. Under specific conditions of extreme density and pressure, gravitational forces could have compressed certain regions beyond the point of recovery, creating these primordial black holes. These ancient objects might continue to drift through space today, invisible and undetected throughout the cosmic void. Some theoretical frameworks suggest they could constitute a significant fraction of dark matter, the mysterious substance that astronomers believe comprises most of the universe's mass. Primordial black holes represent a completely different category from the black holes commonly discussed in astrophysics. Traditional stellar black holes form when massive stars conclude their life cycles through catastrophic collapse. These objects typically possess masses ranging from several solar masses to dozens of times our Sun's mass. However, primordial black holes theoretically formed through entirely different mechanisms during the universe's first moments. This alternative formation process means they need not conform to the size constraints of stellar black holes. Some theoretical models suggest they could be extraordinarily small, potentially matching atomic dimensions while retaining tremendous mass density. This unique combination of minuscule size and enormous mass concentration makes them fascinating subjects for scientific investigation, as they might exhibit behaviors entirely different from conventional black holes. These tiny yet massive objects could potentially illuminate some of the universe's most perplexing questions, including the fundamental nature of dark matter. Unlike their stellar counterparts, which form from dying stars, primordial black holes would have emerged from the primordial chaos of the young universe, predating stellar formation by billions of years. According to theoretical frameworks, minute but significant fluctuations in the early universe's matter distribution could have triggered gravitational collapse in certain regions, creating these black holes. Therefore, primordial black holes originated not from stellar death, but from the extreme conditions of the nascent cosmos. Given their early formation, these objects might be far more abundant than current estimates suggest. Some researchers hypothesize they are distributed throughout the universe, hidden within the vast emptiness of intergalactic space, possibly even within our own galactic neighborhood. Their small size and non-luminous nature would make direct detection nearly impossible, though their gravitational influence might betray their presence. Some scientists propose that primordial black holes could explain one of astronomy's greatest puzzles: dark matter, the invisible substance comprising approximately 85% of the universe's total mass. If this theory proves correct, these ancient black holes might represent the missing component in our understanding of cosmic structure and evolution. Initially, primordial black holes might appear to be purely theoretical constructs, existing only in mathematical models rather than physical reality. After all, no direct observations have confirmed their existence. However, researchers are developing innovative methods to detect these elusive objects, and several promising indicators suggest they might indeed populate the universe. One of the most compelling pieces of evidence comes from gravitational wave astronomy. These space-time ripples generated when massive objects like black holes spiral together and merge have been detected by sensitive instruments in recent years. Some of these gravitational wave signals might originate from primordial black holes that formed during the universe's first moments. If researchers continue detecting gravitational waves from unexpected sources, it could provide strong evidence for the existence of these ancient objects still wandering through the cosmic void. The pattern and frequency of such detections might reveal crucial information about their abundance and distribution. Another promising avenue involves studying the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang approximately 13.8 billion years ago. This ancient light permeates all of space, carrying information about the universe's earliest conditions. If small black holes formed shortly after the Big Bang, they would have influenced this primordial radiation. These influences might leave subtle signatures in the cosmic microwave background, like cosmic fingerprints, that modern telescopes and analytical tools could potentially detect. Identifying such patterns would provide another crucial piece of evidence supporting primordial black hole theories. The mystery deepens when considering primordial black holes' potential role in explaining dark matter. Scientists know dark matter exists through its gravitational effects on visible matter, such as its influence on galactic rotation curves and gravitational lensing of distant galaxies. However, dark matter remains invisible because it neither emits, reflects, nor absorbs electromagnetic radiation. If primordial black holes constitute dark matter, or a significant portion of it, they would help maintain galactic structure and influence cosmic evolution on the largest scales. This would fundamentally alter our understanding of the universe's composition and the forces that shape its evolution. What makes primordial black holes particularly fascinating is their potential formation during the universe's pre-stellar epoch, before stars, planets, or even atoms existed in their current form. While modern black holes typically result from stellar collapse, primordial black holes would have emerged from the chaotic conditions of the newborn universe. If they truly formed during that primordial era, these objects would serve as ancient fossils from the universe's first moments, silent witnesses to the birth of everything we observe today. By studying them, scientists hope to understand the physical conditions that existed when the cosmos was still in its infancy. These black holes could preserve information about the fundamental forces that shape the formation of stars, galaxies, and planetary systems throughout cosmic history. They might even reveal insights about the basic physical laws governing the universe's behavior and evolution. Their significance extends beyond cosmology into fundamental physics. Some researchers believe primordial black holes could help resolve one of science's most profound challenges, reconciling Einstein's general relativity, which describes gravity and large-scale phenomena, with quantum mechanics, which governs subatomic particles. These two theoretical frameworks, while extraordinarily successful in their respective domains, remain incompatible at the deepest level. Scientists have long searched for a unified theory that could bridge this gap, and primordial black holes might provide crucial insights toward achieving this goal. If these ancient black holes exist, they could revolutionize our understanding of physics and cosmology. They might serve as natural laboratories where the extreme conditions necessary to test the boundaries of our current theories actually exist. By studying their properties and behavior, scientists could gain unprecedented insights into the fundamental nature of space, time, matter, and energy. Such discoveries could lead to breakthrough technologies and a deeper understanding of our place in the cosmos. Currently, primordial black holes remain among the most intriguing unsolved mysteries in astrophysics. While scientists have not yet found definitive proof of their existence, the theoretical evidence and potential observational signatures are too compelling to ignore. These objects might be the missing link in our understanding of cosmic evolution, formed in the universe's first moments, and potentially holding answers about galactic formation, dark matter's true nature, and the invisible forces that sculpt the cosmos. As our observational instruments and theoretical models continue to improve, researchers grow increasingly optimistic about solving this cosmic puzzle. With each new gravitational wave detection and cosmic microwave background analysis, they edge closer to determining whether these ancient black holes truly exist and what role they played in shaping the universe we inhabit today. The universe remains unimaginably vast and mysterious, with countless secrets yet to be unveiled. Among these mysteries, primordial black holes stand out as potentially transformative discoveries that could rewrite our understanding of cosmic history. They represent not just fascinating theoretical objects, but possibly the key to unlocking one of the most important stories ever told, the story of how our universe came to exist and evolve into its current magnificent form. When astronomers peer into the deepest regions of space using the most sophisticated telescopes ever constructed, they accomplish something that seems almost magical. They are not simply observing distant celestial objects, they are actually looking backward through time itself. This may sound like science fiction, but it represents one of the most remarkable aspects of how electromagnetic radiation behaves in our universe. Light travels at a finite speed, approximately 300,000 kilometers per second, through the vacuum of space. While this represents an enormous velocity by terrestrial standards, the universe itself is incomprehensibly vast. Consequently, photons from the most distant galaxies require millions or billions of years to complete their journey to Earth. When we observe these remote galaxies, we are not seeing them as they exist in the present moment, but as they appeared in the distant past, sometimes when the universe was still very young. As researchers study these ancient galactic systems, they have made discoveries that challenge fundamental assumptions about cosmic evolution and structure formation. One of the most startling findings involves the presence of supermassive black holes, gravitational monsters so powerful that not even light can escape their influence. What proves truly astonishing is how early in cosmic history these enormous black holes appear to have formed. They existed during epochs when, according to current theoretical models, insufficient time had elapsed for them to reach such tremendous masses through conventional growth mechanisms. Under normal circumstances, black holes begin as relatively modest objects formed from the gravitational collapse of massive stars that have exhausted their nuclear fuel and exploded in spectacular events called supernovae. These stellar mass black holes then grow gradually over millions or billions of years by accreting surrounding gas, dust, and occasionally entire stars. Through this slow process, they can eventually become truly massive objects. However, in these primordial galaxies, scientists have discovered black holes that were already enormous when the universe was still in its infancy, less than 1 billion years after the Big Bang. This presents a significant theoretical challenge. According to our best understanding of black hole physics, achieving such enormous masses requires billions of years of steady growth. These objects need vast amounts of time to gravitationally capture sufficient matter, and this accumulation process cannot be rushed under normal circumstances. Yet these ancient black holes appear to have circumvented the usual waiting period entirely. They achieved supermassive status during an era when galaxies themselves were only beginning to assemble from primordial gas clouds. Some scientists now hypothesize that extraordinary conditions in the early universe may have allowed black holes to grow much more rapidly than they do in the contemporary cosmos. Others suggest that perhaps these black holes did not begin as small stellar remnants at all, but instead formed through entirely different mechanisms, such as the direct gravitational collapse of massive gas clouds without any intermediate stellar phase. Before examining this mystery further, we should first understand what constitutes a supermassive black hole. A black hole represents a region in space-time where gravitational forces have become so intense that nothing, not even electromagnetic radiation traveling at the speed of light, can escape beyond a certain boundary called the event horizon. Once material crosses this invisible threshold, it becomes permanently trapped within the black hole's gravitational well. Black holes exist across a wide range of masses. Some form from the collapse of individual massive stars and contain only a few times our Sun's mass. However, at the opposite extreme are the supermassive black holes, cosmic behemoths containing millions or billions of times the Sun's mass. These represent some of the most massive single objects in the observable universe. These enormous objects do not drift aimlessly through space, but instead reside at the centers of galaxies, including our own Milky Way. They function almost like gravitational anchors for their host galaxies, profoundly influencing stellar motion, star formation rates, and the distribution of gas and dust throughout the galactic disk. Scientists now recognize that supermassive black holes may actually play crucial roles in galactic evolution, controlling how stars move within their gravitational influence, determining where new stellar formation occurs, and regulating the flow of matter throughout the galaxy. Sometimes these black holes generate powerful jets of energy that extend across vast distances, fundamentally altering the structure and dynamics of their entire galactic environment. Our own Milky Way galaxy contains a supermassive black hole known as Sagittarius A star, located at the galactic center. While we cannot observe this object directly due to its non-luminous nature, astronomers can detect its presence by monitoring the orbital motion of nearby stars, which revolve around it at tremendous velocities like celestial dancers caught in an invisible whirlpool. Despite their dark and seemingly empty nature, black holes represent some of the most powerful and influential objects in the universe, serving as cosmic engines that have shaped galactic evolution for billions of years. Some researchers even theorize that without supermassive black holes, galaxies might never have formed at all, or at least not in the complex, organized structures we observe throughout the cosmos today. To better understand the current mystery, let us examine the conventional black hole formation process from its beginning. Most black holes start their existence as stellar mass objects, created when extremely massive stars reach the end of their evolutionary cycles. When such stars exhaust their nuclear fuel, they can no longer maintain the internal pressure necessary to counteract their own gravitational attraction. The stellar core collapses catastrophically, creating what astronomers call a stellar mass black hole. From this initial state, the black hole begins accumulating nearby matter, gradually increasing in mass and size over cosmic timescales. Through billions of years of steady accretion, enhanced by occasional mergers with other black holes, it can eventually achieve supermassive status. However, here lies the fundamental problem that has puzzled astronomers. When they examine the most distant corners of the observable universe, effectively looking back to the earliest epochs in cosmic history, they discover something that defies explanation. Fully mature supermassive black holes already existed less than 1 billion years after the Big Bang, during what represents an extremely early period in cosmic evolution. To provide proper perspective, scientists estimate the universe's current age at approximately 13.8 billion years. This means these gigantic black holes had already achieved enormous masses when the universe was still a small fraction of its present age. This discovery poses a severe challenge to conventional theoretical models. If achieving supermassive status requires billions of years of gradual growth, how could such objects exist when the universe was only 700 to 800 million years old? The situation resembles discovering fully mature oak trees in a forest where seeds were planted mere days earlier. Something fundamental appears to be missing from our current understanding. According to established models, black hole formation should have proceeded much more gradually. First, massive stars would need to complete their entire life cycles, burning through their nuclear fuel reserves, exploding as supernovae, and leaving behind stellar mass black hole remnants. Only then could these objects begin the slow process of growth, feeding on surrounding material or merging with similar objects over billions of years. Yet some of these ancient supermassive black holes seem to have bypassed this entire sequence entirely. They achieved enormous masses long before conventional physics suggests such growth should have been possible. This paradox has forced scientists to consider several revolutionary explanations. Some researchers propose that black holes in the primordial universe may have formed through completely different mechanisms, perhaps emerging directly from the gravitational collapse of massive gas clouds, without any intermediate stellar formation phase. Others suggest the possible existence of primordial black holes, objects that formed during the first seconds after the Big Bang itself, and therefore had access to the entire cosmic timeline for growth and evolution. The discovery of these ancient supermassive black holes has generated tremendous excitement and confusion within the astronomical community. It forces scientists to reconsider fundamental assumptions about cosmic evolution and structure formation. Perhaps black holes do not always follow the slow, methodical growth patterns we have assumed based on contemporary observations. Maybe during the universe's earliest epochs, when conditions were dramatically different from today, some of these objects possessed special formation mechanisms or enhanced growth rates that allowed them to achieve supermassive status much more quickly than current models predict. Regardless of the ultimate explanation, the presence of supermassive black holes in galaxies that formed just a few 100 million years after the Big Bang represents one of the most significant and puzzling discoveries in modern astrophysics. It serves as a humbling reminder that despite all our technological advances and sophisticated theoretical frameworks, the universe continues to harbor profound mysteries that challenge our deepest understanding of cosmic evolution and the fundamental laws of physics that govern reality itself. Black holes grow by gravitationally attracting and consuming nearby material, including gas clouds, dust particles, and occasionally entire stellar systems. As they accumulate more matter over time, they increase in both mass and size. However, during the universe's early epochs, shortly after the Big Bang, relatively little material was available for consumption. The first generation of stars was only beginning to illuminate the cosmic darkness, and galactic structures were in their most primitive stages of assembly. The universe during this period remained young, relatively quiet, and largely devoid of the complex structures we observe today. This raises a fundamental question that has perplexed researchers. If black holes require substantial amounts of surrounding material to achieve growth, how did some of them become incredibly massive so rapidly during an era when very little food was available for consumption? Our current understanding of black hole formation and growth mechanisms fails to adequately explain this phenomenon. According to established theoretical frameworks, achieving supermassive status should require extremely long timescales. Yet scientists have discovered black holes containing millions or billions of solar masses that already existed when the universe was merely a few 100 million years old, representing just a tiny fraction of its current age of nearly 14 billion years. This remarkable and counterintuitive discovery has led researchers to propose that extraordinary processes must have operated during those primordial epochs. Either black holes discovered methods to grow much more rapidly than previously thought possible, or significant gaps remain in our understanding of how the early universe functioned. To address this mystery, scientists have developed several fascinating theoretical explanations. One possibility suggests that certain black holes may have completely bypassed the conventional growth process. While black holes typically form through the gravitational collapse of massive stars that have exhausted their nuclear fuel, some objects in the early universe might have originated from enormous gas clouds, far larger than anything observed in the contemporary cosmos, that collapsed directly into black holes without first undergoing stellar evolution. If this scenario occurred, these black holes would have begun their existence as giants, already possessing masses significantly larger than typical stellar mass objects. This substantial head start would have provided them with considerable advantages in their subsequent growth towards supermassive status. Another theoretical possibility suggests that early universe black holes may have been capable of growing much more rapidly than their modern counterparts. Under normal circumstances, there exists a fundamental limit to black hole growth rates known as the Eddington limit. As a black hole accretes matter, the infalling material releases enormous amounts of energy, creating intense radiation that generates outward pressure, opposing further accretion. This physical balance typically constrains how quickly black holes can grow under standard conditions. However, some scientists speculate that under very special circumstances in the primordial universe, black holes might have exceeded this fundamental limit, achieving growth rates previously considered impossible. If this theory proves correct, it could explain how they reached supermassive status within such compressed timescales. An additional intriguing hypothesis traces back to the universe's very first moments. Some researchers believe that specialized objects called primordial black holes may have formed just moments after the Big Bang, when the cosmos existed as an extraordinarily hot, dense, and chaotic environment. These black holes would have originated not from stellar collapse, but directly from extreme fluctuations in the primordial universe's energy and matter distribution. If they formed with already substantial masses, they would have possessed enormous advantages and could have evolved into supermassive black holes much more rapidly than objects following conventional formation pathways. This scenario resembles entering a marathon race with a significant head start over all other competitors. Yet another theoretical framework suggests that black holes may not have grown in isolation, but instead formed in groups or clusters within the early universe. Over cosmic time, gravitational attractions could have drawn these objects together, leading to rapid collision and merger events. Such processes could have created increasingly massive black holes within relatively short timeframes, potentially fast enough to produce supermassive objects just a few 100 million years after the Big Bang. Perhaps the most intriguing possibility is that these early cosmic giants are attempting to communicate something even more profound about the universe's fundamental nature. Some scientists theorize that understanding these ancient supermassive black holes might lead to revolutionary discoveries in physics, possibly revealing unknown forces, exotic forms of matter, or novel physical processes that enabled accelerated black hole growth beyond our current theoretical comprehension. If any of these scenarios prove accurate, they could completely transform our understanding of cosmic evolution and the fundamental laws governing reality. This is why astronomers express such enthusiasm about the advanced observational tools now available for exploring the universe's most distant regions. One of the most powerful instruments is the James Webb Space Telescope, launched in 2021 and now providing unprecedented views of the cosmos's earliest epochs. By carefully studying these ancient galaxies and their central supermassive black holes, scientists hope to uncover the mechanisms that allowed such enormous objects to exist so soon after cosmic dawn. Each new observation from this revolutionary telescope functions like a window into the distant past, and every discovery brings us incrementally closer to solving one of the universe's greatest puzzles. How did supermassive black holes come into existence so quickly after the Big Bang? Currently, the discovery of these ancient cosmic giants has left scientists simultaneously amazed and bewildered. According to everything we thought we understood about black hole physics, they should not have had sufficient time to exist in their observed forms. Yet, they demonstrably do exist, and their presence fundamentally challenges the foundations of our current understanding of how black holes form, grow, and influence cosmic evolution throughout the universe's history. The discovery of the universe's very first stars takes us on an extraordinary journey deep into cosmic antiquity, so far back in time that we are essentially examining the universe's earliest photographs. These primordial stars, designated by astronomers as population 3 stars, represent incredibly rare and mysterious objects that possess unique characteristics, distinguishing them from all subsequent stellar generations. What makes them particularly special is their composition, consisting entirely of the 2 simplest and lightest elements in the universe, hydrogen and helium. These ancient stars formed during the universe's infancy, not long after the Big Bang itself, during an epoch when everything remained new, chaotic, and filled with tremendous energy. With the remarkable capabilities of the James Webb Space Telescope, scientists now possess the ability to peer further back in cosmic time than ever before possible. This revolutionary instrument functions as a cosmic time machine, enabling researchers to study these primordial stars and explore events that occurred more than 13 billion years ago, providing an unprecedented window into the universe's earliest developmental stages, long before Earth, our solar system, or even the Milky Way galaxy had begun to form. The story of these ancient stellar objects begins with the most significant event in all of cosmic history, the Big Bang, which occurred approximately 13.8 billion years ago and initiated everything we know about space, time, matter, and energy in our observable universe. Approximately 13.8 billion years ago, the universe experienced its most dramatic moment of creation through an event far more profound than any ordinary explosion. This singular occurrence marked the simultaneous birth of time, space, matter, energy, and all the fundamental forces that would govern reality. During the initial minutes following this cosmic genesis, the universe existed in a state of unimaginable temperature and density, forming a turbulent ocean of pure energy and elementary particles so extreme that only the most basic, atomic structures could emerge from the chaos. The first elements to condense from this primordial inferno were hydrogen and helium, along with trace quantities of lithium. Hydrogen atoms, consisting of a single proton paired with 1 electron, represented the simplest possible atomic configuration. Helium followed shortly thereafter, featuring a more complex architecture of 2 protons, 2 neutrons, and 2 electrons. These fundamental building blocks would eventually serve as the raw materials for constructing everything that exists today, including stars, planetary systems, galactic structures, and ultimately biological life itself. During this early epoch, more complex elements such as carbon, oxygen, iron, and gold remained non-existent. These heavier substances would only emerge much later through nuclear processes occurring within the cores of massive stars, where they would be forged like precious metals in cosmic foundries, operating at temperatures of millions of degrees. Following this brief period of elemental creation, the universe entered a prolonged phase of darkness and silence that astronomers term the cosmic dark ages. This extended period lasted hundreds of millions of years, during which the cosmos remained completely devoid of luminous objects. No stars illuminated the void, no galaxies had yet assembled, and no light travelled through the empty expanses of space. Only invisible clouds of hydrogen and helium gas drifted slowly through the cosmic darkness, waiting for the next phase of cosmic evolution to begin. Even during this seemingly quiet period, fundamental forces were working behind the scenes to shape the universe's future. Gravity, the invisible attraction between masses, began its patient but relentless work of drawing scattered gas clouds together into increasingly dense concentrations. As these primordial clouds contracted under their own gravitational pull, they gradually heated up through compression until they reached critical thresholds for nuclear ignition. Then, in one of the most transformative moments in cosmic history, the first stars burst into existence, ending the long night and flooding the universe with light for the very first time. These primordial stellar objects differed dramatically from any stars we observe in the contemporary universe. They were absolutely enormous, burning with incredible intensity and composed exclusively of the hydrogen and helium created during the Big Bang, since no heavier elements had yet been synthesized. Scientists classify these ancient stars as population 3 objects to distinguish them from later stellar generations that incorporated heavier elements produced by their predecessors. These first stars did not merely shine passively, but actively transformed the fundamental character of the universe through a process called cosmic reionization. Before their ignition, the cosmos was filled with thick, opaque clouds of neutral hydrogen gas that prevented electromagnetic radiation from traveling freely across space. When these stellar giants began nuclear fusion in their cores, they emitted intense ultraviolet radiation with sufficient energy to strip electrons from hydrogen atoms throughout the surrounding medium. This process converted neutral hydrogen into an ionized plasma, making the previously opaque universe suddenly transparent to light. This transformation changed the entire appearance and behavior of the cosmos, converting it from a foggy, impenetrable medium into a clear, light-filled expanse. These population 3 stars were not just large by modern standards, but were absolutely gigantic, with many containing hundreds or thousands of times the mass of our Sun. Due to their enormous size, they consumed their nuclear fuel at extraordinary rates. While stars like our Sun can sustain fusion reactions for billions of years, these ancient giants exhausted their energy reserves in just a few million years, representing mere instants on the cosmic timescale. Their deaths were correspondingly spectacular. When these massive stars depleted their nuclear fuel, they exploded in supernova so powerful that they illuminated entire regions of the early universe. During these catastrophic events, the first heavy elements, including carbon, oxygen, silicon, iron, and gold, were synthesized in the extreme conditions of the explosion and subsequently scattered throughout space. These newly created elements proved absolutely essential for cosmic evolution, serving as the chemical foundation for forming more complex structures, including rocky planets, atmospheric compositions, and eventually the molecular building blocks necessary for biological processes. In this sense, the death of each population 3 star represented not an ending, but a creative beginning, dispersing the chemical ingredients required for everything that would follow, including the eventual emergence of life. Studying these ancient stars presents one of the greatest challenges in modern astronomical research. Because they existed so long ago and at such vast distances, their light has traveled for billions of years to reach Earth, becoming extremely faint and stretched by cosmic expansion in the process. Direct observation of individual population 3 stars remains nearly impossible with current technology. Instead, astronomers search for indirect evidence of their existence and influence, such as the large-scale effects they had on their surrounding environments. One crucial signature involves the formation of massive ionized regions, enormous bubbles of space where radiation from these first stars stripped electrons from surrounding hydrogen gas. By analyzing the size, shape, and distribution of these ionized bubbles, researchers can infer important characteristics about the stars that created them, including their masses, luminosities, and the speed at which they transformed the early universe. The significance of population 3 star research extends far beyond historical curiosity about cosmic origins. These studies are fundamental to understanding how life became possible in the universe. Without these first stellar generations, the heavy elements that comprise planets, atmospheres, oceans, and living organisms would never have existed. By investigating their properties and evolution, scientists move closer to answering some of humanity's most profound questions about our cosmic origins and the conditions that made biological existence possible. These ancient stars also provide crucial insights into the formation of galaxies, supermassive black holes, and other large-scale cosmic structures. By understanding how population 3 stars were born, lived, and died, researchers can reconstruct the entire narrative of cosmic evolution, from the first glimmers of light to the complex network of galaxies and stellar systems we observe throughout the modern universe. Thanks to revolutionary instruments like the James Webb Space Telescope, astronomy is entering an unprecedented golden age of discovery. This remarkable observatory is already providing new insights into how the earliest galaxies and stellar populations formed and evolved. Future generations of even more powerful telescopes will extend these investigations further, potentially allowing direct detection of population 3 stellar remnants or their chemical signatures. Such discoveries would be equivalent to opening time capsules sealed at the very beginning of cosmic history, providing direct connections to the ancient past and unprecedented insights into the physical conditions that shaped our universe. The study of population 3 stars represents one of the most exciting frontiers in contemporary astrophysics, offering a direct pathway to understanding the origins of everything we observe in the cosmos today. Heavy elements throughout the universe are synthesized through a fundamental process called nucleosynthesis, where atomic nuclei combine under extreme conditions found in stellar cores and explosive events. The most massive elements are created through specialized mechanisms such as the rapid neutron capture process, which occurs when neutron stars collide or during the most violent stellar explosions known to science. Nucleosynthesis itself involves the formation of new atomic nuclei from protons and neutrons, the fundamental building blocks of all matter in the universe. According to current scientific understanding, the very first atomic nuclei formed just minutes after the Big Bang through primordial nucleosynthesis. Approximately 20 minutes after cosmic creation, the universe had expanded and cooled sufficiently that high-energy particle collisions became less frequent, allowing only the simplest nuclear reactions to occur, and leaving behind primarily hydrogen and helium with small quantities of lithium and deuterium. Subsequently, stellar evolution and explosive events created the diverse array of elements observed throughout the modern universe through a process astronomers call cosmic chemical evolution. However, the universe remains predominantly composed of hydrogen and helium, with heavier elements comprising only a small fraction of the total cosmic mass, though these trace constituents are essential for forming complex structures and enabling biological processes. Stars function as massive nuclear factories where lighter elements fuse into heavier ones within their cores, releasing tremendous amounts of energy in the process. This stellar nucleosynthesis operates through fusion reactions that create progressively heavier elements, including iron and nickel in the most massive stars. The products of these nuclear processes generally remain confined within stellar interiors, unless expelled through stellar winds or explosive events. Neutron capture processes, including both rapid and slow mechanisms, are responsible for synthesizing even heavier elements beyond iron. When massive stars explode as supernova, they create additional elements, particularly those with atomic numbers between oxygen and rubidium, through the combination of previously synthesized materials released from stellar cores, intense fusion reactions occurring during the explosion itself, and rapid neutron capture processes facilitated by the extreme neutron densities generated during the event. Recent discoveries have revealed that neutron star mergers, where 2 ultra-dense stellar remnants collide and merge, also produce substantial quantities of heavy elements through rapid neutron capture. These cosmic collisions release enormous amounts of neutron-rich material that rapidly transforms into heavier elements through successive neutron absorption and radioactive decay processes. Another mechanism for element production involves cosmic ray spallation, where high-energy cosmic ray particles strike atomic nuclei and fragment them into lighter elements. This process is particularly important for creating certain light elements such as lithium, beryllium, and boron, which are not efficiently produced by stellar nucleosynthesis. Cosmic ray spallation can occur in interstellar space, on asteroid surfaces, or even within Earth's atmosphere, contributing to the inventory of elements found on our planet. On Earth, additional atomic nuclei form through radiogenic processes, where naturally occurring radioactive elements such as uranium, thorium, and potassium undergo gradual decay over geological timescales, producing daughter isotopes that contribute to the terrestrial element abundance patterns. Tracing cosmic history back to its origins, scientists believe that the fundamental constituents of matter, protons, and neutrons emerged from an extremely hot particle soup approximately 13.8 billion years ago. As the universe cooled during its first few minutes, these particles combined to form the initial atomic nuclei, including hydrogen, helium, and trace amounts of lithium and beryllium. However, elements like carbon could not form during this epoch because the physical conditions were unsuitable, and nucleosynthesis essentially ceased after about 20 minutes, as continued cosmic expansion reduced temperatures and densities below critical thresholds. Early stellar populations utilized these primordial light elements to synthesize heavier ones through nuclear fusion processes. These initial building blocks, created during Big Bang nucleosynthesis and cosmic ray interactions, provided the raw materials for the first generation of stars. Over millions of years, cosmic ray bombardment caused spallation reactions in interstellar gas and dust, creating additional quantities of light elements that would be incorporated into subsequent stellar generations. Carbon, which could not be produced during primordial nucleosynthesis, was first created in massive stars through the triple alpha process, representing a crucial milestone in cosmic chemical evolution. The synthesis of progressively heavier elements requires extremely high temperatures and pressures, conditions found only in stellar cores and explosive environments. This process began when hydrogen and helium from the Big Bang gravitationally collapsed to form the first stars approximately 500 million years after cosmic creation. Since that epochal moment, stellar formation has continued throughout galaxies, gradually enriching the interstellar medium with heavier elements. The primary mechanisms responsible for element creation include Big Bang nucleosynthesis, stellar nucleosynthesis, supernova nucleosynthesis, and rare events such as neutron star mergers. Some isotopes are produced through the gradual radioactive decay of unstable elements over cosmic timescales. The heavier elements, ranging from carbon to the heaviest naturally occurring and artificially created substances, were synthesized through nuclear reactions involving fundamental forces operating between atomic nuclei. These processes include nuclear fusion, both rapid and slow neutron capture, nuclear fission, and various forms of radioactive decay, including beta decay processes that transform the nuclear composition. The stability of different atomic nuclei, determined by their specific combinations of protons and neutrons, strongly influences how these nuclear reactions proceed. This fundamental relationship makes the study of cosmic nuclear synthesis essential for scientists investigating stellar evolution and nuclear physics, a field known as nuclear astrophysics. Initially, early scientists hypothesized that all chemical elements were created simultaneously during the universe's formation, but no clear physical mechanism could explain such a scenario. Gradually, it became apparent that hydrogen and helium far exceeded all other elements in cosmic abundance, comprising nearly 98% of all matter in the solar system and throughout the observable universe, while all other elements collectively account for less than 2% of the total mass. Oxygen and carbon were identified as the next most abundant elements after hydrogen and helium, and researchers noted that lighter elements, particularly those composed of whole multiples of helium-4 nuclei, showed significantly higher abundances than their neighbours on the periodic table. In 1920, Arthur Stanley Eddington first proposed that stars generate energy by fusing hydrogen into helium, and speculated that heavier elements might also be synthesized in stellar interiors, though this revolutionary idea was not widely accepted because the underlying nuclear physics was not yet understood. The detailed mechanisms of hydrogen fusion were not elucidated until just before World War II, when Hans Bethe explained how hydrogen converts to helium through nuclear chain reactions in stellar cores. Following the war, Fred Hoyle made groundbreaking contributions to understanding how heavier elements form in stars, developing comprehensive theories explaining how all elements more massive than hydrogen were synthesized from primordial material. Hoyle proposed that hydrogen was continuously created throughout the universe from vacuum energy without requiring a specific origin event, and his work explained how elemental abundances increased over cosmic time as galaxies aged and evolved. This theoretical framework was expanded during the 1960s by scientists including William Fowler, Alistair Cameron, and Donald Clayton. A seminal 1957 paper by Margaret Burbidge, Geoffrey Burbidge, Fowler, and Hoyle summarized major advances in the field, describing novel pathways for heavy element synthesis in stellar interiors and providing observational strategies for astronomers to study these processes. The Big Bang theory itself was originally proposed in 1931 by Georges Lemaitre, a Belgian physicist and priest who argued that the expanding universe must have originated from an extremely dense initial state he called the primeval atom. He theorized that tracing cosmic expansion backward in time would lead to this singular point before space and time existed as we understand them. Hoyle coined the term Big Bang during a 1949 BBC radio broadcast, though he claimed it was not intended as a disparaging nickname, but rather as a vivid metaphor to distinguish this theory from alternative steady-state models. Lemaitre's concept proved crucial for explaining the observed cosmic abundances of helium and the presence of deuterium and other light elements found not only in stellar atmospheres, but also in the interstellar medium. Ultimately, both Lemaitre's and Hoyle's contributions to understanding cosmic element synthesis proved essential for developing our modern comprehension of universal chemical composition and evolution. The theory of nucleosynthesis attempts to explain the observed abundances of different chemical elements and their isotopes throughout the universe by invoking natural physical processes operating under extreme conditions. A primary motivation for developing nucleosynthesis theory came from the peculiar patterns observed when elemental abundances are plotted against atomic number. When these abundances are displayed graphically, the resulting curve appears extremely irregular, with some elements being millions of times more abundant than their immediate neighbors on the periodic table. One of the most significant achievements in this research was the compilation of cosmic elemental abundances by Hans Suess and Harold Urey, based on pristine compositions found in meteorites that had remained largely unaltered since the solar system's formation. Their abundance table, displayed on a logarithmic scale, helped smooth the dramatic variations in elemental concentrations by accommodating the enormous range of values spanning many orders of magnitude. Various astrophysical processes contribute to nucleosynthesis, with most occurring within stellar interiors during different phases of stellar evolution. The chain of nuclear fusion reactions in stars, collectively known as hydrogen burning, can proceed through two primary pathways: the proton-proton chain reaction or the carbon-nitrogen-oxygen cycle. Subsequent burning phases include helium burning, carbon burning, neon burning, oxygen burning, and silicon burning, with these fusion processes capable of synthesizing elements up to iron and nickel, which represent the most stable nuclear configurations per unit mass. For elements heavier than iron, alternative processes become necessary. Within stellar environments, a neutron capture process called the slow process can gradually build heavier nuclei, while more extreme events such as supernova explosions or neutron star collisions facilitate other mechanisms including rapid neutron capture, proton capture, and photo-disintegration processes, where high-energy gamma rays break apart existing nuclei. Stellar nucleosynthesis represents the fundamental process creating new atomic nuclei within stellar interiors throughout a star's evolutionary lifetime, and it is essential for understanding how elements from carbon through iron are distributed throughout galaxies. Stars function as enormous nuclear furnaces, where lighter elements like hydrogen and helium undergo fusion to produce progressively heavier elements as the stellar core contracts and heats up during evolutionary phases. As stellar cores reach higher temperatures and densities, they become capable of synthesizing increasingly massive elements. One of the most crucial reactions involves carbon production through the triple alpha process, where 3 helium-4 nuclei combine to form carbon-12. Carbon synthesis is particularly important because it enables the creation of even heavier elements and facilitates the release of free neutrons within stellar cores, initiating slow neutron capture processes that gradually convert iron peak elements into much heavier species, including gold and uranium. Elements synthesized within stellar interiors do not remain permanently trapped, but are eventually expelled into the interstellar medium. As stars age and evolve, they begin losing mass through stellar winds, powerful streams of particles flowing outward from stellar surfaces. For lower mass stars, this mass loss occurs during the asymptotic giant branch phase, when stars shed their outer layers to form planetary nebulae. For much more massive stars, dramatic element dispersal occurs when they reach the end of their evolutionary tracks and explode as supernovae, representing one of the primary mechanisms for distributing heavy elements throughout the cosmos. The first compelling evidence that stars serve as cosmic element factories came from observations that interstellar gas, the raw material for new star formation, was becoming progressively enriched in heavy elements over cosmic time. This meant that stars born later in galactic history contained higher concentrations of elements heavier than hydrogen and helium compared to stars that formed during earlier epochs. A crucial discovery occurred in 1952 when astronomers detected the element technetium in the atmosphere of a red giant star. Technetium is radioactive with a relatively short half-life, meaning it could not have survived since the galaxy's formation, but must have been synthesized recently within that particular star. This observation provided direct evidence that nuclear reactions were actively occurring in stellar interiors. Additional support came from discoveries of enhanced barium abundances in certain stars, particularly those in advanced evolutionary phases, known as asymptotic giant branch stars. These evolved stars showed much higher barium concentrations than younger stellar populations, indicating that slow neutron capture processes were operating within their interiors to gradually build heavier elements over extended timescales. Modern astronomy has access to even more remarkable evidence through presolar grains, microscopic solid particles that formed in stellar atmospheres and were later incorporated into meteorites that eventually reached Earth. These grains formed before our solar system existed and carry unique isotopic signatures that reveal the nuclear processes occurring within their parent stars as those ancient objects reach the final stages of their evolutionary lives. Supernova nuclear synthesis occurs during the extremely energetic and violent environment of stellar explosions, where elements from silicon through nickel are created through rapid fusion reactions. These reactions involve silicon-28 nuclei in a state called quasi-equilibrium, where the material is not completely stable, but contains large quantities of silicon-28 that can rapidly rearrange under the extreme conditions. This quasi-equilibrium concept represented a major theoretical breakthrough in understanding how intermediate mass elements are synthesized during explosive events. It replaced earlier incorrect theories and built upon important foundational work by Fred Hoyle in 1954. Beyond quasi-equilibrium processes, there also exists a much more rapid mechanism called the R process, or rapid neutron capture process, where atomic nuclei quickly absorb large numbers of neutrons to create elements much heavier than the iron peak. The R process was first described theoretically by scientists including Seeger, Fowler, and Clayton, and it represents a major pathway for synthesizing very heavy elements including uranium and thorium. Remarkably, R-process nucleosynthesis can occur even in stars composed almost entirely of hydrogen and helium, something that was once thought impossible but is now understood to play a crucial role in creating the heaviest elements throughout the universe. Evidence for R-process nucleosynthesis comes from observations of extremely old stars that formed in metal-poor galactic environments. These ancient stars still contain detectable quantities of R-process elements, demonstrating that this powerful nuclear process must have operated in stellar environments regardless of the initial heavy element content of their host galaxies. There also exists an RP process, or rapid proton capture process, similar to R-process nucleosynthesis, but involving the rapid capture of protons rather than neutrons. Scientists continue investigating this mechanism to understand its importance in cosmic element synthesis, though it may contribute to the production of certain rare isotopes under specific astrophysical conditions. During supernova explosions, atomic nuclei with equal numbers of protons and neutrons are produced in large quantities due to the extreme nuclear physics operating under these conditions. This balance tends to create more stable nuclear configurations, for example when oxygen and silicon undergo fusion during the explosion to produce calcium-40, which contains equal numbers of protons and neutrons. However, if the resulting nuclei are more massive than iron while still maintaining equal proton and neutron numbers, they tend to be unstable and undergo radioactive decay after the explosion concludes. When this occurs, they transform into more stable isotopes such as iron-56, chromium-52, and titanium-48, simultaneously releasing characteristic gamma rays that can be detected by astronomical instruments. The detection of these gamma-ray signatures has become a powerful tool for gamma-ray astronomy and provides compelling evidence for explosive nucleosynthesis occurring in stellar environments. One of the most significant discoveries came from the supernova that exploded in 1987, designated SN 1987A, when astronomers successfully detected gamma-ray emission lines corresponding to radioactive isotopes, including cobalt-56 and cobalt-57. This observation provided direct proof that explosive nuclear synthesis actually occurs in supernova and represented a major milestone for the field of nuclear astronomy. The gamma-ray data collected from supernova 1987A was so scientifically valuable that it influenced the design specifications for NASA's Compton Gamma Ray Observatory, demonstrating the importance of these observations for advancing our understanding of cosmic nuclear synthesis. Supernovae also contribute to heavy element production through the creation of pre-solar dust grains that form as the explosion debris cools and condenses. These microscopic particles carry the chemical fingerprints of the explosive events that created them, including unusual isotopes such as titanium-44 that serve as diagnostic tracers of supernova nucleosynthesis. The discovery of titanium-44 in pre-solar grains confirmed theoretical predictions that supernovae contribute to cosmic dust production while providing detailed insights into the mechanisms of explosive nucleosynthesis. Even today, by analyzing the distinctive isotopic compositions preserved within these ancient dust grains, scientists continue unlocking the secrets of how elements throughout our universe were synthesized during the violent deaths of massive stars. For thousands of years, human beings have gazed upward at the night sky with profound wonder and insatiable curiosity, asking one of the most fundamental and enduring questions in all of human experience. Are we alone in this vast universe? As people throughout history contemplated the countless points of light scattered across the darkness above, they imagined distant worlds that might be similar to Earth or completely different, where other forms of life might exist and flourish. The night sky, with its brilliant stars distributed across seemingly infinite expanses of darkness, has always represented one of the greatest mysteries confronting human consciousness and scientific inquiry. Throughout human history, the celestial tapestry above has captivated the imaginations of scientists, philosophers, adventurers, and visionaries from every culture and era. With countless billions of stellar objects blazing across the immense expanse of the cosmos, many have theorized that some fraction of these distant suns must harbor planetary companions circling in their gravitational embrace. These hypothetical worlds might possess temperate climates, abundant water resources, and perhaps even flourishing ecosystems teeming with life. Yet for millennia, this remained purely speculative, an inspiring vision supported only by hope and imagination rather than concrete evidence. No human observer had ever definitively identified a planetary body orbiting beyond the boundaries of our own solar system. This situation underwent a revolutionary transformation during the final decades of the 20th century. Through remarkable technological breakthroughs, including space-based observatories with unprecedented sensitivity and ambitious exploratory missions reaching into the depths of the solar system, astronomical researchers began uncovering extraordinary revelations. They established beyond doubt that Earth occupies no unique position as the sole planet-bearing system in the universe. Over the past several decades, scientists have verified the existence of thousands upon thousands of worlds orbiting distant stars, completely reshaping our understanding of planetary formation and cosmic architecture. These remote celestial bodies are designated exoplanets, representing planetary systems centered around stars other than our Sun. This groundbreaking discovery has fundamentally altered humanity's perspective on both the scale of the universe and our species' place within the grand cosmic narrative. The revelation has simultaneously expanded our conception of the universe's vastness, while filling it with unprecedented possibilities and wonder. Among the numerous thousands of confirmed exoplanets catalogued thus far, only a relatively small subset appears to possess environmental conditions potentially suitable for supporting life as we understand it. These favorable characteristics include appropriate surface temperatures, the presence of liquid water, and stable atmospheric compositions capable of maintaining habitable conditions over geological timescales. However, the search for potentially life-bearing worlds continues to accelerate and expand. With each new detection and characterization, researchers edge incrementally closer to addressing one of humanity's most profound and enduring questions about whether biological processes might exist elsewhere among the stars. Exoplanets represent planetary bodies that complete orbital cycles around stellar objects other than our solar system's central star. These distant worlds exhibit tremendous diversity in their physical characteristics and compositions. Some are diminutive and rocky, sharing structural similarities with Earth's geological makeup. Others are colossal spheres composed primarily of gaseous materials, resembling scaled versions of Jupiter's massive bulk. Still others possess such exotic properties that they seem to belong in the realm of speculative fiction rather than observational astronomy. Astronomical surveys have revealed exoplanets existing in environments previously considered impossible for planetary formation or survival. Some worlds experience perpetual frigid conditions, locked in endless winter cycles far from their parent stars. Others endure blazing temperatures with surface features including molten rock oceans and volcanic activity spanning entire hemispheres. In the most extreme documented cases, researchers have identified planets where atmospheric conditions are so intense that metallic elements vaporize and subsequently condense into precipitation, creating iron rain falling from superheated skies. The inaugural discovery of confirmed exoplanets occurred in 1992 under circumstances that surprised the entire astronomical community. These first detected worlds were found orbiting a pulsar, representing a type of collapsed stellar remnant that emits powerful beams of electromagnetic radiation across space. These planetary bodies bore no resemblance to the familiar worlds of our own solar system, yet their existence demonstrated a crucial principle that planetary formation can occur under a much broader range of conditions than previously imagined. Subsequently, in 1995, scientists identified 51 Pegasi b, marking the first confirmed exoplanet discovered orbiting a main sequence star similar to our Sun. This gas giant world opened an entirely new chapter in astronomical research and planetary science. Since that pivotal moment, astronomers have catalogued more than 5,000 exoplanets, with new discoveries being added to the registry on a regular basis. Advanced observational instruments, including the James Webb Space Telescope, enable scientists not only to detect these distant worlds, but also to analyze their atmospheric compositions in search of chemical signatures or biosignatures that might indicate biological activity. The diversity of exoplanets defies simple classification, yet researchers have developed systematic categories based on planetary composition, size, mass, and orbital characteristics relative to their host stars. Gas giants represent one of the most prominent categories of exoplanets discovered to date. These massive worlds consist predominantly of hydrogen and helium, the two lightest elements in the periodic table. Jupiter and Saturn from our own solar system serve as familiar examples of gas giant architecture. These worlds achieve such enormous dimensions that more than 1,300 Earth-sized planets could fit within Jupiter's volume alone. Unlike terrestrial planets, gas giants lack solid surfaces that could support conventional landing operations. Any probe attempting to descend through their atmospheric layers would encounter progressively denser and hotter conditions, eventually reaching regions where hydrogen gas becomes compressed into metallic liquid states under extreme pressure. Scientists theorize that solid rocky cores may exist deep within these giants, though confirming this hypothesis remains impossible due to the prohibitive conditions that would destroy any investigative spacecraft. Gas giants often represent the first planetary detections in newly surveyed stellar systems because their massive size enables them to block significant amounts of starlight during transit events, a detection method that allows identification of worlds separated by many light-years from Earth. Some exoplanetary gas giants exhibit properties even more extreme than Jupiter or Saturn, particularly the category known as hot Jupiters that orbit extremely close to their parent stars, resulting in atmospheric temperatures that cause violent boiling of gaseous components. Ice giants like Neptune and Uranus represent another subset of gas giant worlds, characterized by substantial concentrations of water, ammonia, and methane compounds frozen in their atmospheric and interior structures. While gas giants might initially appear too extreme to support biological processes, studying their properties provides valuable insights into planetary formation mechanisms and evolutionary pathways. Additionally, These worlds raise intriguing possibilities about whether their satellite systems might harbour habitable conditions, similar to Jupiter's icy moon Europa. Neptune-like planets, sometimes designated mini-Neptunes, constitute another fascinating category of exoplanetary objects. These worlds share structural characteristics with Uranus and Neptune from the outer regions of our solar system, consisting primarily of gaseous materials without solid surfaces accessible for exploration. The distinctive blue coloration of Uranus and Neptune results from methane concentrations within their atmospheric compositions, which also generate dramatic weather patterns, including powerful storm systems and high-velocity wind currents. These ice giant worlds contain substantial quantities of frozen compounds, including water ice, ammonia, and methane, justifying their classification within the ice giant category. Mini-Neptunes typically possess smaller dimensions than massive gas giants like Jupiter, while still significantly exceeding Earth's size and mass. Their atmospheric envelopes are substantial but less extensive and dense than those surrounding the largest gas giants. Current astronomical surveys suggest that Neptune-like planets may actually represent one of the most abundant planetary types throughout the galaxy, making them extremely significant for understanding typical planetary system architecture. Each of these worlds possesses unique characteristics, with some featuring heavy cloud-covered atmospheres that trap thermal energy and create humid environmental conditions, while others maintain lighter, more variable atmospheric compositions that generate complex weather systems. Although mini-Neptunes lack accessible solid surfaces, they may harbour exotic atmospheric phenomena, or even subsurface ocean layers hidden beneath their gaseous envelopes. While these worlds typically do not maintain the powerful magnetic field systems or massive storm complexes characteristic of larger gas giants, they can still exhibit significant atmospheric activity and dynamic weather patterns that make them scientifically fascinating subjects for detailed study. Super-Earths represent another remarkable category of exoplanets, characterized by masses larger than Earth but smaller than Neptune-sized worlds. These planets significantly exceed our homeworld's dimensions and mass, while remaining substantially smaller than gas giants like Neptune or Jupiter. The designation Super-Earth refers specifically to size and mass characteristics, rather than compositional properties or habitability potential. Some super-Earths may possess solid, rocky surfaces similar to Earth's geological structure, while others might be enveloped by thick atmospheric layers or extensive ice sheets that obscure any underlying solid components. One of the most compelling aspects of super-Earth worlds involves their potential for supporting biological processes, particularly those that orbit within their star's habitable zone, where temperatures permit liquid water to exist on planetary surfaces. These worlds might be capable of sustaining diverse ecosystems, ranging from microscopic organisms to more complex biological structures. Another intriguing characteristic of super-Earths involves their enhanced gravitational fields, resulting from increased planetary mass, which would create stronger surface gravity compared to Earth's conditions. This enhanced gravity could complicate potential human exploration, while simultaneously providing advantages such as improved atmospheric retention that might shield against harmful cosmic radiation. Super-Earths exhibit tremendous diversity in their potential characteristics and environmental conditions. Some might feature vast planetary oceans covering their entire surface area, while others could possess dense atmospheric compositions similar to Venus that trap substantial thermal energy through greenhouse effects. Some may contain valuable mineral resources or exotic chemical compounds not found elsewhere in known planetary systems. Due to their increased size and mass, super-Earths likely maintain hotter, more geologically active interior structures compared to Earth. This enhanced internal activity could drive more frequent volcanic processes that, over millions of years, help establish stable atmospheric compositions through outgassing of various compounds. If super-Earths possess magnetic field systems comparable to Earth's protective magnetosphere, they could effectively shield their surfaces from dangerous solar wind particles, enhancing their potential habitability. Astronomical surveys have already identified numerous super-Earth candidates in distant stellar systems, and advanced telescopic observations are enabling increasingly detailed characterization of these worlds. Some of the most well-known examples, including Kepler, 22b and TOI 700d, have generated significant scientific interest because they appear to orbit within their star's habitable zones where conditions might support liquid water and potentially biological activity. Terrestrial planets represent the rocky worlds found within our solar system, including Earth, Mars, Venus, and Mercury. These planetary bodies are distinguished by their predominantly solid compositions of rock and metal, providing stable surface features that contrast dramatically with gas giants composed primarily of volatile materials without accessible solid boundaries. The solid geological structure of terrestrial planets makes them particularly significant for astrobiological research, focused on identifying environments where life might exist or have existed in the past. Earth serves as the archetypal example of a life-bearing terrestrial world, making it the primary reference point for evaluating the habitability potential of similar rocky exoplanets discovered around distant stars. Mars has become a major focus of scientific investigation due to its rocky surface geology and abundant evidence of ancient fluvial activity, including dried riverbeds, lake basins, and mineral deposits that indicate substantial liquid water existed on its surface during earlier epochs. Many researchers theorize that Mars may have possessed suitable conditions for supporting biological processes during its early history, prompting extensive robotic exploration missions designed to search for evidence of past or present microbial life. Venus presents an intriguing case study as Earth's so-called sister planet due to similar size and density characteristics, yet it maintains extremely hostile surface conditions with crushing atmospheric pressure and temperatures exceeding 450 degrees Celsius, caused by a runaway greenhouse effect. Despite these harsh conditions, studying Venus provides valuable insights into atmospheric evolution and planetary climate dynamics that inform our understanding of habitability limits. Mercury, the smallest terrestrial planet in our solar system, experiences extreme temperature variations due to its proximity to the Sun and lack of substantial atmospheric buffering, ranging from scorching daytime heat to frigid nighttime cold. Research on Mercury helps scientists understand planetary formation processes and surface modification mechanisms operating in high radiation environments. The shared characteristic of solid surfaces makes terrestrial planets particularly valuable for habitability assessment, as these worlds could potentially support liquid water reservoirs and the complex chemistry required for biological processes. Scientists continue searching for Earth-like exoplanets within the habitable zones of distant stars, where rocky worlds might maintain temperate conditions suitable for supporting life as we understand it. Not every planetary environment possesses the necessary characteristics for supporting biological activity. For a world to potentially harbour life, it must maintain specific conditions that allow liquid water to persist on or near its surface over extended periods. Water's fundamental importance stems from its role as the universal solvent required by all known biological processes, from simple bacterial metabolism to complex multicellular organism functions. Scientists evaluate several critical factors when assessing whether distant exoplanets might possess habitability potential. The habitable zone, frequently called the Goldilocks zone, represents a specific orbital range around a star where planetary surface temperatures remain moderate enough to support liquid water, without causing it to freeze solid or boil away completely. This orbital zone represents the optimal distance where water can maintain its liquid phase, creating opportunities for biological chemistry to develop and flourish over time. If a planet orbits too close to its parent star, like Venus in our solar system, excessive stellar radiation creates surface temperatures hot enough to vaporize any water present, leaving behind a desiccated, sterile environment unsuitable for life. Conversely, if a planetary orbit extends too far from its star, like Mars experiences in our solar system, insufficient stellar energy reaches the surface to maintain liquid water, causing any moisture to freeze into solid ice deposits that cannot support active biological processes. Earth maintains its position within the optimal habitable zone around our Sun, receiving just the right amount of stellar energy to support liquid water in oceans, lakes, rivers, and atmospheric vapor that enables the complex water cycle essential for terrestrial life. This perfect orbital positioning allows Earth to maintain diverse aquatic environments that serve as habitats for countless species while providing the liquid medium necessary for all biological chemistry. Without this precisely calibrated distance from our star, Earth would either experience scorching heat that boils away all water or frozen conditions that lock moisture into unusable ice formations. A planet's atmospheric composition functions like a protective envelope that moderates surface temperatures and shields the world from harmful space radiation. This gaseous layer acts as both insulation that prevents extreme temperature fluctuations and a barrier that filters dangerous, high-energy particles from reaching the planetary surface. Earth's atmosphere contains a carefully balanced mixture of gases, with oxygen supporting aerobic respiration for most complex life forms, and carbon dioxide contributing to temperature regulation through the greenhouse effect. This greenhouse warming helps maintain Earth's surface temperature within ranges suitable for liquid water, though excessive carbon dioxide concentrations could create dangerously hot conditions like those observed on Venus. The Moon provides a stark example of how the absence of atmospheric protection affects planetary habitability. Without any gaseous envelope, lunar surface temperatures swing between extreme heat exceeding 250 degrees Fahrenheit during daylight hours and bitter cold below -280 degrees Fahrenheit during the 2-week lunar night, making it impossible for liquid water or biological processes to exist. Venus demonstrates the opposite extreme, where an extremely dense carbon dioxide atmosphere creates an intense greenhouse effect that traps solar energy so efficiently that surface temperatures reach approximately 900 degrees Fahrenheit, hot enough to melt lead and far too extreme for any known form of life. For optimal habitability, planetary atmospheres must maintain precise compositional balances that provide adequate thermal regulation without becoming too thin to retain heat or too thick to avoid overheating. Earth's atmospheric composition represents this delicate equilibrium that enables diverse biological ecosystems to thrive. Earth possesses another crucial characteristic for maintaining habitability in the form of its magnetic field, which functions as an invisible shield protecting the planet from harmful solar radiation. Our star continuously emits streams of high-energy particles known as solar wind that could gradually strip away planetary atmospheres if not deflected by magnetic protection. Mars provides a cautionary example of what can happen when a planet loses its magnetic field protection. Early in its history, Mars possessed a substantial magnetic field, but this protective system eventually weakened and disappeared, leaving the planet vulnerable to direct solar wind bombardment over millions of years. Without magnetic shielding, energetic solar particles gradually eroded Mars's atmospheric envelope, transforming it from a potentially habitable world with a thicker atmosphere and possible liquid water surface features into the cold, dry, thin atmosphere planet we observe today. Scientific evidence suggests that ancient Mars may have possessed Earth-like conditions including flowing rivers, standing water bodies, and perhaps even primitive biological activity before losing its protective magnetic field. Earth's magnetic field continues protecting our planet's atmosphere from solar wind erosion, while also deflecting potentially harmful cosmic radiation that could damage biological organisms. This magnetic protection represents one of several factors that make Earth uniquely suitable for supporting complex life over geological timescales. Even when exoplanets orbit within the habitable zone of their parent stars, they still require additional conditions to support biological activity, most importantly the presence of liquid water. While frozen water ice might exist on various exoplanets throughout the galaxy, only liquid water provides the chemical medium necessary for the complex molecular interactions that define life as we understand it. Liquid water serves as the ideal solvent for biochemical reactions because it remains stable across a wide temperature range while dissolving many different compounds necessary for metabolic processes. Earth's diverse aquatic environments, from vast oceans to small freshwater streams, demonstrate water's crucial role in supporting biological diversity and enabling evolutionary development over billions of years. Scientists studying exoplanets focus their efforts on detecting evidence that might indicate liquid water presence, whether in the form of surface oceans, underground aquifers, or atmospheric water vapor signatures. These investigations require sophisticated analytical techniques, including spectroscopic analysis of exoplanet atmospheres using space-based telescopes capable of detecting specific molecular signatures associated with water compounds. The search for liquid water on distant worlds represents one of the most challenging aspects of exoplanet science, requiring precise measurements of planetary temperatures, atmospheric compositions, and orbital characteristics to determine whether conditions might support water in its liquid phase rather than frozen or gaseous states. The characteristics of host stars play a fundamental role in determining whether their planetary systems can support habitable worlds. Stellar properties including size, temperature, luminosity, and evolutionary stage all influence the potential for planets to maintain conditions suitable for liquid water and biological activity over extended periods. Very massive stars burn their nuclear fuel at extremely rapid rates, producing intense luminosity but short lifespans measured in millions rather than billions of years. While these stellar giants create powerful energy output, their brief existence provides insufficient time for complex biological evolution to occur on any orbiting planets before the star exhausts its fuel and undergoes catastrophic collapse. Conversely, very small, cool stars known as red dwarfs burn their fuel slowly and can maintain steady energy production for tens of billions of years, far exceeding our Sun's expected lifetime. However, their low luminosity means that planets must orbit very close to receive adequate heating, potentially causing problems such as tidal locking, where one hemisphere permanently faces the star while the other remains in perpetual darkness. The most promising stellar candidates for hosting habitable planets are main sequence stars similar to our Sun, which provide steady energy output over billions of years while maintaining luminosity levels that can warm planets at comfortable orbital distances. These solar-type stars create stable, habitable zones that remain relatively constant throughout their long lifespans, allowing ample time for biological processes to develop and evolve. Slightly smaller stars, known as K-dwarf stars, also represent excellent candidates for supporting habitable planets. While cooler than Sun-like stars, K-dwarfs maintain stable energy production and exceptionally long lifetimes that could support biological evolution over even longer timescales than solar-type systems. The vast distances separating exoplanets from Earth make direct visual observation impossible for most of these distant worlds. Instead, astronomers employ ingenious indirect detection methods that analyze subtle changes in starlight or stellar motion to infer the presence of orbiting planets that remain invisible to even our most powerful telescopes. These sophisticated techniques enable scientists to discover and characterize planetary systems throughout the galaxy, despite the enormous challenges posed by interstellar distances and the overwhelming brightness of host stars that would normally obscure any planetary signals. The transit method represents one of the most successful approaches for detecting exoplanets, operating on the principle of observing temporary dimming of starlight when a planet passes directly between its host star and Earth-based observers. This technique resembles watching a small shadow cross in front of a bright light source, causing measurable but tiny decreases in the star's apparent brightness that can be detected by sensitive photometric instruments. Astronomers employ sophisticated techniques to identify planets orbiting distant stars, beginning with careful observation of stellar objects located hundreds or thousands of light years from our solar system. These celestial bodies emit intense luminosity across vast cosmic distances. When an orbiting planet crosses between Earth and its host star, it creates a measurable reduction in the star's apparent brightness. Consider this planetary body as a small celestial object temporarily obscuring portions of stellar radiation during its orbital passage. This stellar dimming effect remains subtle yet detectable, occurring at regular intervals corresponding to the planet's orbital period around its parent star. The magnitude of light obstruction correlates directly with planetary dimensions and the fraction of stellar surface area blocked during transit events. Researchers identify these systematic brightness variations through continuous stellar monitoring programs extending across multiple observation periods. Recognition of consistent dimming patterns at predictable intervals indicates the presence of an orbiting companion causing these photometric variations. That companion represents a planetary body transiting across the stellar disk. Through precise photometric measurements, scientists determine planetary characteristics, including size estimates. Larger planetary bodies obstruct greater amounts of stellar radiation, while smaller worlds produce correspondingly minor brightness reductions. NASA's Kepler Space Telescope served as a primary instrument for implementing this detection methodology. Kepler conducted systematic sky surveys spanning several years, monitoring photometric variations across thousands of stellar targets simultaneously. Kepler's observational campaigns resulted in the identification of thousands of previously unknown exoplanetary systems throughout our galactic neighborhood. Each discovered world orbits its respective host star within diverse stellar environments across the Milky Way galaxy. Transit photometry enables astronomers to determine fundamental planetary properties, including orbital periods and potential habitability assessments based on stellar distance relationships. This methodology has facilitated groundbreaking discoveries in astrobiology research programs seeking evidence of extraterrestrial life. Following initial transit detections, researchers employ additional observational techniques to characterize atmospheric compositions, planetary masses, and surface conditions. Each transit event provides valuable data contributing to our understanding of distant planetary systems. The radial velocity technique, alternatively termed the stellar wobble method, represents another sophisticated approach for detecting remote planetary companions invisible to direct observation. This methodology exploits gravitational interactions between orbiting planets and their host stars. Planetary companions exert gravitational forces on their parent stars throughout their orbital cycles, analogous to a cosmic tug-of-war scenario. During orbital motion, planets generate small but measurable gravitational perturbations, causing their host stars to exhibit subtle positional oscillations. These stellar movements remain imperceptible to casual observation, yet produce detectable effects through precise instrumentation. Despite their enormous masses, stars respond to planetary gravitational influences by executing small circular or elliptical trajectories corresponding to their planetary companions' orbital motions. Detection of these stellar wobbles requires extraordinarily sensitive spectrographic equipment capable of measuring minute positional variations with exceptional precision. Astronomers track stellar positions and analyze spectral characteristics to identify gravitational perturbations caused by unseen planetary companions. These spectral variations result from the Doppler effect, the same physical phenomenon causing audible frequency changes in passing vehicle engines. Stellar motion toward Earth produces spectral blue shifts toward shorter wavelengths, while recession creates red shifts toward longer wavelengths. Measuring these subtle spectral color variations enables scientists to confirm planetary gravitational influences on stellar motion. This technique allows detection of planetary companions located at tremendous distances, often millions or billions of light-years away, without direct visual confirmation. The radial velocity method successfully identifies planets too distant for direct imaging or too faint compared to their brilliant host stars for telescopic observation. This approach reveals crucial planetary characteristics, including mass estimates, orbital distances, and gravitational binding strengths between planetary and stellar components. Scientists extract detailed information about invisible worlds without visual confirmation. This methodology has proven instrumental in discovering numerous exoplanetary systems orbiting stars beyond our solar system. Radial velocity surveys have identified hundreds or potentially thousands of previously unknown planetary companions throughout our galactic region. This technique expands our cosmic perspective by revealing hidden worlds awaiting future exploration missions. Direct imaging methodology provides the extraordinary opportunity to photograph actual exoplanetary systems located beyond our solar neighborhood. These distant worlds orbit stars separated by vast interstellar distances throughout the galaxy. However, stellar brilliance creates significant observational challenges, as intense starlight overwhelms the faint reflected radiation from orbiting planetary companions. This observational difficulty resembles attempting to discern a dim light source positioned adjacent to an extremely bright spotlight. Overcoming this fundamental challenge requires cutting-edge telescope technology, incorporating specialized light-blocking systems, These advanced coronagraphic instruments selectively suppress overwhelming stellar radiation while preserving faint planetary signals for detailed analysis. This sophisticated observational approach functions like specialized optical filters, enabling clear vision of subtle details despite intense background illumination. Although direct imaging remains technically demanding and infrequently employed, successful implementations provide invaluable scientific data about exoplanetary characteristics, including size measurements, atmospheric compositions, and surface condition assessments. These rare photographic achievements enable comprehensive analysis of potentially habitable worlds, allowing researchers to evaluate life-supporting capabilities and identify similarities with planets within our own solar system. Direct imaging creates actual visual records of distant planetary systems, advancing our comprehension of the vast cosmic environment surrounding Earth. Gravitational microlensing represents an ingenious and powerful astronomical technique, enabling detection of otherwise invisible planetary systems throughout the galaxy. Understanding this methodology requires examining the fundamental physics underlying gravitational light deflection phenomena. Consider a planetary body drifting through interstellar space, positioned between Earth and a distant background star. Normally, stellar radiation travels in straight lines across cosmic distances toward terrestrial observers. However, when a foreground planet passes directly between Earth and the background star, extraordinary optical effects occur. The planet's gravitational field functions as a natural magnifying lens, bending and focusing the background star's light to create temporary brightening effects visible from Earth. This light-bending phenomenon results from gravity's ability to curve space-time geometry around massive objects. Einstein's general relativity theory demonstrates that gravitational fields from planets and stars distort the fabric of space itself. When planetary gravity intercepts stellar radiation, it redirects the light path through space-time curvature, producing observable magnification effects called gravitational microlensing events. This detection method excels at revealing planetary companions inaccessible through conventional observational techniques. Many planets remain too distant, too small, or too faint for detection through transit photometry or radial velocity measurements. Microlensing bypasses these limitations by exploiting gravitational effects rather than electromagnetic radiation analysis. Gravitational microlensing events resemble discovering hidden cosmic treasures during rare celestial alignments. When planetary gravity focuses background starlight, Earth-based instruments record characteristic brightness variations, revealing planetary properties including mass, distance, and orbital characteristics through detailed photometric analysis. This methodology extends beyond planetary detection to investigate exotic cosmic phenomena, including black holes and neutron stars, capable of producing similar gravitational lensing effects. Because microlensing reveals planets in remote galactic regions, this technique opens unprecedented opportunities for exploring previously inaccessible cosmic territories and advancing astronomical knowledge beyond current limitations. Astronomers have identified numerous exoplanetary candidates potentially capable of supporting biological processes, each possessing unique characteristics warranting intensive scientific investigation. Among the most promising discoveries stands Proxima Centauri b, orbiting our nearest stellar neighbor, located approximately 4 light-years from the solar system. Proxima b occupies the circumstellar habitable zone, a region where surface temperatures could permit liquid water stability. While this positioning suggests favorable conditions, researchers continue investigating whether the planet possesses atmospheric protection necessary for biological sustainability and surface habitability. The TRAPPIST-1 system presents a remarkable configuration located roughly 40 light-years distant, containing 7 terrestrial-sized planetary companions. 3 of these worlds orbit within their star's habitable zone, where appropriate temperatures might allow liquid water existence. TRAPPIST-1 represents one of the most scientifically significant systems for astrobiology research, commanding intensive observational attention from the international astronomical community. Kepler 442b, classified as a super-Earth exoplanet, resides within its host star's habitable zone approximately 1,200 light-years away. This world ranks among the highest priority habitability candidates based on size and orbital characteristics, suggesting optimal temperature ranges and potential atmospheric conditions conducive to biological processes. LHS 1140b, a rocky planetary body situated about 40 light-years distant, represents another compelling discovery. This world likely possesses substantial atmospheric density and potentially stable liquid water reservoirs, making it an exceptional candidate for life detection programs. Its rocky composition suggests Earth-analog surface conditions potentially suitable for biological development. These examples represent a fraction of the exoplanetary population currently under scientific scrutiny. Each discovery advances our understanding of biological potential throughout the universe, making these distant worlds extraordinarily significant for astrobiology research programs. Advanced space telescopes like the James Webb Space Telescope, JWST, now provide unprecedented capabilities for analyzing exoplanetary atmospheric compositions through sophisticated spectroscopic techniques. Scientists systematically examine these distant worlds seeking specific gaseous compounds, including oxygen, methane, and carbon dioxide, molecules closely associated with biological processes on Earth. Oxygen production typically results from photosynthetic organisms, methane often originates from living systems, and carbon dioxide participates in fundamental biological cycles. Although definitive proof of extraterrestrial life remains elusive, the discovery of thousands of potentially habitable worlds has intensified scientific excitement about astrobiology prospects. The sheer abundance of habitable zone planets suggests that biological processes may not be unique to Earth. Somewhere within the cosmic vastness, another world might harbor thriving ecosystems awaiting future discovery and characterization. Rogue planets, also designated free-floating planets or isolated planetary mass objects, represent large celestial bodies exhibiting planetary characteristics while lacking gravitational association with any host star. Unlike conventional planets orbiting stellar companions, these objects drift independently through interstellar space, unbound by stellar gravitational fields. Their designation as rogue reflects their wandering nature through galactic environments. These isolated worlds originate through various astrophysical processes. Some form within conventional planetary systems similar to Earth or Jupiter, but experience gravitational ejection through catastrophic events, including planetary collisions, close gravitational encounters, or powerful dynamical interactions. Following ejection, these bodies traverse interstellar space independently, permanently separated from their original stellar environments. Alternative formation scenarios suggest some rogue planets condense directly within interstellar regions, never experiencing stellar gravitational binding. These objects develop through independent accretion processes in star-forming regions throughout galactic environments. Current estimates suggest the Milky Way galaxy contains billions, or potentially trillions, of these mysterious wandering worlds. Future space missions, including the Nancy Grace Roman Space Telescope, will conduct comprehensive surveys to quantify rogue planet populations and investigate their fundamental properties throughout our galactic neighborhood. Interestingly, some objects classified as rogue planets may represent failed stellar formation products rather than conventional planetary bodies. These objects might have initiated star formation processes, but lacked sufficient mass to achieve nuclear fusion ignition. The International Astronomical Union proposes designating these bodies as sub-brown dwarfs, representing intermediate objects between planets and stars. Scientific literature employs various terminology for these enigmatic objects. Early research described isolated planetary mass objects and free-floating planets in technical publications, while microlensing studies commonly use the simpler rogue planet designation. Popular media frequently employs alternative terms including wandering planets, starless planets, or orphan planets for public communication. The first significant discoveries occurred around 2000, when multiple research teams identified isolated planetary mass objects in star-forming regions. A United Kingdom team led by Lucas discovered several objects using infrared observations in the Orion Nebula, while a Spanish group led by Zapatero Osorio identified similar objects in the Sigma Orionis cluster using the Keck telescope. Spectroscopic follow-up observations in 2001 confirmed these groundbreaking discoveries. Earlier potential detections in 1999 by a Japanese team led by Owasa in the Chameleon. Cloud required additional confirmation through 2004 spectroscopic analysis by American researchers to verify their planetary nature. Rogue planet detection employs two primary methodologies: gravitational microlensing and direct infrared imaging. Microlensing exploits gravitational light-bending effects when rogue planets pass between Earth and background stars, creating temporary brightness amplification events detectable through photometric monitoring programs. In 2011, Takahiro Sumi from Osaka University led a comprehensive microlensing survey using telescopes in New Zealand and Chile, monitoring over 50 million stars throughout the Milky Way. The study utilized the 1.8-meter MOA telescope at Mount John Observatory and the 1.3-meter University of Warsaw telescope at Las Campanas Observatory, recording 474 microlensing events with 10 consistent with Jupiter mass rogue planets. This analysis estimated approximately 2 Jupiter mass rogue planets per star in our galaxy. Extended studies suggested even higher ratios, including smaller planetary masses, with some proposals indicating 100,000 times more rogue planets than stars when including sub-Earth mass objects. A 2017 study by Moroz from Warsaw University Observatory, 6 times larger than previous surveys, suggested more conservative estimates of approximately 0.25 Jupiter mass rogue planets per star. The landmark September 2020 discovery of Ogle 2016 BLG 1928 marked the first Earth mass rogue planet detection through microlensing techniques. Direct imaging provides complementary observational capabilities by photographing rogue planets through their thermal emission signatures. This methodology requires determining planetary brightness and age to estimate masses accurately, presenting significant technical challenges for distant objects. Most identified rogue planets reside in young star-forming regions where age estimates prove more reliable. These objects typically exhibit ages less than 200 million years, with masses exceeding 5 Jupiter masses, often classified as L-dwarf and T-dwarf brown dwarfs, some older, cooler. Bi-dwarf objects possess masses between 8 to 20 Jupiter masses. The nearest rogue planet candidate, WISE 0855-0714, lies approximately 7.27 light-years away, providing opportunities for detailed characterization studies. Understanding rogue planet origins requires distinguishing between ejected planetary systems and in-situ formation scenarios based on kinematic and compositional analysis. High-velocity objects like WISE J08 30+2837, moving at 100 km per second, and WISE 1534-1043, traveling at 200 km per second, suggest potential ejection origins, though spectral analysis indicates some may represent old brown dwarfs rather than true rogue planets. Current scientific consensus suggests most isolated planetary mass objects represent the low-mass end of star formation processes rather than ejected planetary systems, though definitive origins remain uncertain pending improved observational capabilities and larger statistical samples. Most rogue planets experience extremely low temperatures due to the absence of stellar heating sources, unlike planets within conventional solar systems. Despite frigid conditions, these objects emit detectable thermal radiation in infrared wavelengths, invisible to human vision, but accessible through specialized space-based observatories. NASA's James Webb Space Telescope represents the most advanced instrument for detecting faint infrared signatures from cold rogue planets throughout interstellar space. Unlike conventional telescopes optimized for visible light detection, JWST operates primarily in infrared wavelengths, enabling observations through interstellar dust and gas obscuration. JWST's unprecedented sensitivity allows detection of extremely faint thermal emission from rogue planets drifting through remote galactic regions. These objects remain invisible to optical telescopes due to their isolation from illuminating stellar sources, but their residual heat signatures provide observable targets for infrared astronomy programs. Giant planets like Jupiter produce strong radio emission through magnetospheric processes involving charged particle interactions within powerful magnetic fields. Jupiter's magnetic field, significantly stronger than Earth's, traps solar wind particles in radiation belts, generating detectable radio signals observable from terrestrial radio telescopes. Rogue planets possessing strong magnetic fields might similarly produce radio emission detectable through sensitive radio astronomy techniques. Since rogue planets lack stellar illumination for optical detection methods, radio observations could provide alternative detection pathways for isolated planetary systems throughout the galaxy. Specialized radio telescopes designed for weak signal detection might identify rogue planet magnetospheric emission, expanding discovery techniques beyond optical and infrared methodologies. Radio detection would provide entirely new approaches for planetary discovery, potentially revealing populations invisible to conventional astronomical surveys. This methodology could advance understanding of planetary magnetic field generation and evolution in isolated environments, providing insights into magnetospheric protection mechanisms essential for atmospheric retention and potential habitability assessments, even for starless planetary systems. Planetary ejection processes that remove planets from their original stellar systems could similarly affect associated satellite systems. Moons orbiting ejected planets might remain gravitationally bound throughout interstellar transit, creating isolated planet-moon systems drifting through galactic environments without stellar companions. However, gravitational perturbations from massive objects including nearby stars or planetary encounters could disrupt planet-moon gravitational binding, liberating individual moons into independent interstellar trajectories. These liberated satellites would become rogue moons, isolated objects no longer orbiting any planetary or stellar companion. Such rogue moons represent an entirely unexplored population of small bodies potentially scattered throughout galactic space, accessible only through future advances in detection sensitivity and observational techniques capable of identifying extremely faint thermal signatures from isolated subplanetary mass objects. These isolated celestial bodies drift silently through interstellar void, completely detached from any gravitational anchor. Rogue moons present far greater detection challenges compared to their planetary counterparts due to their diminutive size and absence of intrinsic luminosity. Unlike stars or certain planetary bodies that generate their own radiant energy, these wandering satellites remain virtually invisible without external illumination sources. Their detection represents an extraordinary technical challenge for contemporary astronomical instrumentation. Most telescopic systems prove inadequate for identifying such faint non-luminous objects dispersed throughout galactic space. These elusive bodies can only be observed when positioned near bright astronomical sources that provide sufficient contrast for visual identification. Despite these observational difficulties, discovering rogue moons would revolutionize our comprehension of planetary system formation and dissolution processes. The existence of satellites separated from their parent planets demonstrates the dynamic, turbulent nature of cosmic environments. Such discoveries would reveal that gravitational interactions affect all celestial bodies regardless of size, sometimes producing unexpected orbital disruptions that liberate moons from their planetary hosts. Rogue moons represent the universe's forgotten wanderers, silently traversing galactic regions while harboring crucial information about cosmic evolutionary processes. Identifying even a single specimen, or perhaps entire populations, would inaugurate unprecedented chapters in astronomical understanding and expand our knowledge of celestial mechanics throughout the galaxy. Although rogue planets lack stellar companions, they remain scientifically significant for comprehensive astrophysical investigations. Initially, the prospect of biological activity on isolated worlds drifting through frigid interstellar darkness without stellar warmth might seem impossible. However, researchers propose that under specific conditions, life could potentially survive on starless planetary environments. Rogue planets possessing substantial atmospheric density could effectively trap internal heat generated by planetary core processes. This atmospheric greenhouse effect might maintain surface temperatures sufficient for liquid water stability, a fundamental requirement for known biological processes. Some isolated worlds might harbour extensive subsurface oceans, similar to those discovered beneath the icy shells of Europa and Enceladus, Jovian and Saturnian satellites respectively. These concealed aquatic environments could provide thermally stable, protected habitats where biological systems might persist despite complete isolation from stellar radiation. Through detailed rogue planet investigations, scientists can enhance understanding of planetary formation mechanisms and long-term evolutionary processes. The prevalence of planetary ejection from original stellar systems indicates that planetary formation represents a significantly more chaotic and stochastic process than previously understood. This realization could fundamentally alter theoretical models describing stellar and planetary birth, evolution, and eventual destruction throughout galactic environments. Dark matter represents one of cosmology's most profound enigmas, an invisible constituent comprising the majority of universal mass, yet remaining undetectable through conventional observational methods. Some researchers hypothesize that rogue planets might contribute to resolving this cosmic mystery. Their substantial masses enable gravitational lensing effects that bend light from distant stellar sources, potentially providing indirect evidence for dark matter distributions. Recent discoveries have significantly advanced rogue planet research. In 2021, astronomers identified a Jupiter-sized, isolated planet traveling independently through the Milky Way galaxy, completely separated from any stellar system. This remarkable discovery provided researchers with unprecedented opportunities to study these enigmatic worlds in detail. Subsequently, 2023 investigations suggested that rogue planets might actually outnumber stars throughout the universe, a startling revelation that challenges conventional understanding of planetary formation and distribution across cosmic scales. This surprising conclusion revolutionizes theoretical frameworks describing planetary populations and their prevalence in galactic environments. Future space missions, particularly NASA's Nancy Grace Roman Space Telescope, promise to dramatically expand rogue planet discovery capabilities over the coming decades. These advanced observational platforms, combined with revolutionary detection technologies and analytical techniques, will likely transform our cosmic perspective and deepen understanding of these wandering worlds that continue inspiring both professional astronomers and public fascination with space exploration. The most extraordinary cosmic mystery involves something completely imperceptible to human senses: dark matter. This invisible scaffolding permeates the universe, creating vast, unseen networks across cosmic distances. Direct visual observation remains impossible, even with the most sophisticated telescopic instruments available to modern astronomy. Scientists confirm dark matter's existence not through direct detection, but through its profound gravitational influence on surrounding cosmic structures. When astronomers observe galactic rotation patterns, they discover anomalous behavior. These stellar systems rotate at velocities that should theoretically cause complete structural disintegration based on visible matter calculations alone. However, galaxies maintain structural integrity through invisible gravitational binding forces. This unseen influence represents dark matter, a hidden cosmic component providing the gravitational cohesion necessary for galactic stability. Unlike conventional matter that emits or reflects electromagnetic radiation, dark matter remains completely transparent to all wavelengths of light. The designation dark reflects its optical invisibility rather than any inherently sinister characteristics. Despite remaining undetectable through electromagnetic observation, dark matter's gravitational effects provide measurable evidence of its existence. This resembles inferring wind patterns through observing leaf movement rather than direct atmospheric visualization. The observable universe, including stars, planets, interstellar gas, cosmic dust, and all biological matter, comprises merely 5% of total cosmic content. All spectacular galaxies and luminous nebulae captured in astronomical photography represent an infinitesimal fraction of universal composition. Dark matter constitutes approximately 27% of cosmic content, while an even more mysterious component called dark energy comprises the remaining 68%. While dark matter provides gravitational attraction, dark energy generates repulsive forces that accelerate universal expansion at increasing rates. Consequently, the majority of cosmic existence remains invisible to human observation. These imperceptible forces, dark matter and dark energy, represent the fundamental architects of universal structure, continuously shaping everything from subatomic particles to galactic superclusters throughout 13 billion years of cosmic evolution since the Big Bang's initial moment. Understanding dark matter's crucial role requires examining cosmic origins, nearly 13.8 billion years ago. During those primordial moments, the universe existed as an intensely hot, chaotic plasma containing fundamental particles and pure energy in constant, turbulent motion. Even during this early epoch, dark matter already influenced cosmic development. As universal expansion continued and temperatures decreased, dark matter began gravitationally clustering into concentrated regions. Despite remaining invisible, its gravitational influence attracted conventional matter, including gas and dust, toward these dark matter concentrations. This process facilitated the formation of primordial stars and galactic structures throughout cosmic history. Dark matter functioned as an invisible architectural blueprint, guiding universal development and evolution. Without this fundamental scaffolding, galaxies might never have coalesced, leaving the universe as an empty, dispersed collection of isolated particles. Dark matter halos represent one of the most remarkable discoveries in modern cosmology. These enormous invisible structures surround entire galactic systems like vast protective bubbles composed entirely of dark matter. Every galaxy, including our Milky Way, exists within such invisible envelopes. These halos provide essential gravitational stability, preventing galactic disintegration during rotational motion. Scientific evidence suggests every observed galaxy possesses an associated dark matter halo. Without these structures, galaxies would lack sufficient gravitational binding to maintain coherence and might never have formed originally. Gravitational lensing provides powerful observational evidence for dark matter's existence. This phenomenon occurs when light from distant galaxies becomes deflected by massive intervening objects like galaxy clusters, creating cosmic magnification effects similar to optical lenses. Careful analysis of light deflection patterns reveals significantly more mass present than visible matter alone can account for. This additional invisible mass represents dark matter, providing the extra gravitational influence necessary to explain observed lensing effects. Gravitational lensing constitutes some of the strongest empirical evidence supporting dark matter's reality. These observations demonstrate that universal mass content far exceeds directly observable matter, revealing extensive dark matter distributions throughout galactic clusters and cosmic structures. The cosmic microwave background, CMB, provides additional crucial evidence. This ancient radiation represents remnant energy from the Big Bang, essentially a photographic snapshot of the universe when it was approximately 380,000 years old. Detailed CMB analysis reveals subtle patterns indicating dark matter's presence during early cosmic epochs, demonstrating its role in facilitating initial galactic formation processes. Contemporary scientific efforts focus intensively on determining dark matter's fundamental composition. Leading theoretical candidates include WIMPs, weakly interacting massive particles, hypothetical entities that barely interact with ordinary matter, making direct detection extraordinarily challenging. Despite detection difficulties, researchers employ various experimental approaches including massive underground detectors, powerful particle accelerators like the Large Hadron Collider, and sophisticated space-based instruments designed to identify these elusive particles. Although direct dark matter detection remains elusive, each experimental attempt, successful or unsuccessful, advances scientific understanding incrementally. Even minor breakthroughs could revolutionize cosmic comprehension and unlock entirely new physical principles governing universal behavior. Advanced space missions, including the James Webb Space Telescope, provide unprecedented opportunities to observe primordial galactic formation when dark matter initially shaped cosmic structures. These observations allow scientists to examine galaxies as they appeared billions of years ago, closer to dark matter's earliest cosmic influence. Terrestrial research continues through increasingly sensitive detection equipment placed in deep underground facilities, isolated from interfering radiation sources, designed to capture the faintest possible dark matter interaction signatures. This comprehensive research program aims toward the ultimate goal of understanding this invisible substance that provides universal gravitational cohesion. Success extends beyond solving scientific mysteries to fundamentally rewriting cosmic origin stories, evolutionary processes, and ultimate universal destiny. Dark matter may remain hidden from direct observation, but its influence has guided universal development since the earliest moments of existence. As scientific investigation continues, humanity approaches discoveries that could transform understanding of space, time, and fundamental physical reality. This scientific journey represents just the beginning of comprehensive cosmic exploration and discovery. Dark energy presents cosmology's most perplexing enigma, a mysterious force that scientists have studied extensively for decades while remaining fundamentally incomprehensible. Current understanding reveals dark energy comprises approximately 68% of total universal content. Visualizing the universe as an enormous pie, dark energy represents the largest slice by far. Yet this dominant component remains completely invisible, intangible, and unmeasurable through direct methods. Its existence becomes apparent only through observable effects on cosmic structures we can detect. This resembles feeling an invisible force pushing from behind. You experience the effect without identifying the source. Dark energy similarly influences universal behavior, while remaining imperceptible to direct observation. Dark energy's discovery story began during the late 1990s when two independent research groups made revolutionary observations that transformed cosmological understanding. They investigated supernovae, catastrophic stellar explosions occurring during certain star deaths. These explosions produce consistent brightness levels, allowing astronomers to use them as cosmic distance markers. However, supernova observations revealed shocking results. These explosions appeared much farther away than theoretical predictions suggested, indicating that universal expansion wasn't merely continuing, but actually accelerating over time. This unexpected acceleration required explanation through some mysterious repulsive force, dark energy, actively pushing cosmic structures apart. This discovery revolutionized cosmological theory, challenging the assumption that gravity represented the primary universal force. While gravity attracts matter together, dark energy produces opposite effects by forcing everything apart through repulsive interactions. Dark energy's fundamental nature remains unknown. Current understanding suggests that space itself isn't empty void, but rather resembles stretchable fabric. This cosmic fabric can expand, carrying embedded matter to increasingly distant separations. Imagine invisible forces pulling this fabric from all directions, causing accelerating expansion. Dark energy appears to function through this mechanism, stretching cosmic space at ever-increasing rates. A useful analogy involves an inflating balloon where surface points move progressively farther apart as expansion continues. Galaxies function like these surface points, not traveling through space independently, but carried apart by expanding space-time itself. Dark energy exhibits bizarre characteristics unlike any known forces. Gravity provides attractive interactions. Electromagnetic forces create charge attractions, but dark energy generates purely repulsive effects. Even more mysteriously, this repulsive force apparently strengthens over time. Several theoretical explanations attempt to describe dark energy's nature. Einstein's cosmological constant represents one possibility, originally proposed to balance universal equations before expansion discovery. Initially considered Einstein's greatest mistake, this concept gained renewed relevance following dark energy observations. This theory proposes dark energy as a constant force uniformly filling all space without temporal variation, essentially an invisible energy field permeating the entire universe. Quintessence theory suggests dark energy might vary across space and time rather than remaining constant. This concept envisions cosmic energy fluid flowing throughout the universe with variable strength, similar to dynamic magnetic fields that continuously shift and evolve. Additional theories propose dark energy connections to extra-dimensional space. Our observable reality contains 3 spatial dimensions plus time, but additional hidden dimensions might exist beyond direct perception. These concealed dimensions could influence universal behavior in unknown ways, with dark energy resulting from interdimensional interactions. Alternative theories suggest dark energy might not represent a separate force, but rather indicate incomplete understanding of gravitational behavior across cosmic scales. Gravity might function differently at enormous distances compared to local Earth-based observations. If this proves accurate, apparent dark energy effects might simply reflect limited gravitational comprehension rather than representing distinct cosmic forces. Despite dark energy's mysterious nature, scientists employ ingenious investigative methods. Supernova and distant galaxy observations remain crucial tools. By measuring their light characteristics and distances, researchers determine universal expansion rates, the original dark energy discovery method. Cosmic microwave background analysis provides additional insights. This ancient Big Bang radiation contains subtle patterns revealing early universal conditions. Studying these patterns helps scientists understand dark energy's influence on cosmic shape and development over billions of years. Major research projects advance dark energy understanding. The Dark Energy Survey uses powerful telescopes to observe billions of galaxies and measure dark energy's cosmic influence. The European Space Agency's Euclid mission takes detailed galactic measurements across the universe, hoping to discover new dark energy characteristics and operational mechanisms. Dark energy's most fascinating aspect involves its potential influence on universal destiny. This isn't merely a distant, abstract concept, but actively determines cosmic fate billions of years into the future. Scientific observations show dark energy continuously accelerates universal expansion over time. If this mysterious force maintains current behavior, it could produce dramatic cosmic changes in the extremely distant future. Imagine scenarios many billions of years hence when dark energy becomes sufficiently powerful to stretch everything apart. This Big Rip concept suggests universe expansion could become so rapid that galaxies separate completely, followed by individual stellar disruption. Eventually, even planets, moons, and atomic structures might be torn apart if the force becomes sufficiently extreme. While resembling science fiction, some scientists consider this scenario plausible if dark energy continues strengthening. Alternatively, dark energy might weaken or disappear over time. If this occurs, universal expansion could halt or reverse, leading to the Big Crunch scenario, where all cosmic structures gradually collapse back together, potentially recreating conditions similar to the original Big Bang. Currently, no definitive predictions exist regarding universal destiny because dark energy remains profoundly mysterious. Scientists have only recently begun understanding its existence through observable effects on galactic motion and expansion rates. Dark energy cannot be seen, touched, or measured directly. It resembles an invisible force hiding in plain sight while influencing everything around it. Current knowledge confirms dark energy as one of science's greatest mysteries, comprising roughly 70% of universal content. This means the majority of cosmic existence remains incomprehensible to human understanding. Dark energy might represent constant, unchanging energy filling all space, or it could function as a dynamic, evolving force. Some scientists speculate about connections to hidden spatial dimensions beyond human perception. Regardless of its true nature, dark energy represents a crucial component in understanding universal mechanics and ultimate destiny. As telescopic technology advances and scientific knowledge expands, humanity may finally uncover this invisible force's secrets. When that breakthrough occurs, we will approach complete understanding of universal fate itself.